Welcome to this course on demand planning and forecasting. In many organizations, demand planning still faces a few common challenges. Forecasts are built in Excel, but they lack structure. Accuracy is measured, but inconsistently. And decision-making often relies on intuition rather than data. This course is designed to address these challenges in a practical and a structured way. You won't just learn forecasting concepts. You'll learn how to actually build, evaluate, and improve forecast in a real-world setting. We'll start off the course by building a strong foundation in theoretical concepts surrounding demand planning and forecasting. You'll learn how demand planning works in real organizations. We'll explore forecasting techniques such as moving average analysis, time series analysis, and regression analysis. We'll also cover how to analyze forecast performance and understand accuracy analysis metrics like mean absolute error and bias percentage. But this course doesn't just stop at theory. You'll also learn how to implement these concepts efficiently using the right tools. You'll first build a fully automated forecasting model in Excel, a model in which you input historical data, select a few forecasting techniques, and the model automatically generates the forecast for next 12 months. Afterwards, we'll learn how to use Power Query to clean and transform data. We'll learn visualization principles and create interactive dashboards in Power BI. We'll also explore DAX formula language in Power BI to build measures for dynamic analysis. Along the way, you'll reinforce your learning through hands-on exercises and quizzes. This is a hands-on course. You won't just watch the videos, you'll build models, you'll work with data, and by the end of the course, you'll create something tangible. This course is ideal for aspiring demand planners, supply chain professionals, business analysts, and Excel and Power BI users who are looking to apply their skills to real-world scenarios. Even if you're not currently in a demand planning role, but if your work involves forecast budgets or data analysis, you'll find this course extremely helpful. So if you're looking to move beyond theory and build practical forecasting skills, be confident with data and improve decision-making, then you're in the right place. Welcome everyone. In this video, I'm going to walk you through the course outline and structure. In this course, we take a structured and practical approach to learning demand planning and forecasting. The goal is not just to understand concepts, but also to help you build, evaluate, and present forecast in a way that reflects real-world business scenarios. Let me walk you through how the course is structured. The course is divided into 13 modules. Module 1 to 2 focus on the fundamentals and foundations. Module 1 is the course overview. This is where we are right now. And in Module 2, we'll do a quick introduction to demand planning. You'll understand what demand planning really is, how forecasting works in organizations, and why forecasting is important for businesses. This section builds the foundation for everything that follows. Next, we'll move into forecasting itself. In Module 3, we will explore some commonly used forecasting techniques. We'll look into moving average analysis, time series forecasting, simple and multiple linear regression. Along with the concepts, we will also learn how to implement these techniques in Microsoft Excel. Then in Module 4, Forecast Segmentation and Governance, we'll take it a step further by understanding why different products require different forecasting approaches and how to apply the right technique based on the business context. We will also cover forecast governance and understand how forecasting is typically managed in organizations. Once you understand the techniques, we'll move into implementation. In Module 5, you'll build a fully automated forecasting model in Excel. In this model, once you input actual historical data and select appropriate forecasting techniques, the model will automatically generate a 12-month rolling forecast. This reflects how forecasting models are built in real business environments and also helps to strengthen your Excel skills. Next, we're going to focus on preparing and structuring data for visualization. In Module 6, we set the stage for how forecasts should be presented, and also we'll get an introduction to Power BI. Then in Modules 7 and 8, we're going to cover Power Query and data modeling, where you will learn how to clean and transform data, combine multiple files, and build scalable data models. This module will give us essential learning for working with real-world complex datasets. After that, we move into analysis and visualization. In Module 9, Introduction to DAX, you'll learn how calculations work in Power BI. DAX is a key part of Power BI. Having a strong understanding of DAX will help you create advanced measures such as accuracy metrics and comparisons between different forecast cycles. In Module 10, Business Presentation and Visualization Principles, we'll focus on learning how to design clear and effective visuals and avoid unnecessary complexity. Finally, in Module 11, you'll bring everything together by building an interactive dashboard in Power BI. This dashboard will allow you to compare forecast numbers across different forecast cycles and support in decision making. In final part of the course, we focus on performance evaluation. In Module 12, Accuracy and Performance Analysis, you'll learn how to measure forecast performance using forecast error and bias. And in the final module, you'll apply these concepts to build dynamic accuracy dashboards, compare forecasts across different periods, and generate actionable insights. By the end of this course, you'll have a complete understanding of demand planning, from building forecasts to analyzing performance and presenting insights. The course is designed to be practical, structured, and easy to follow, so you can apply these skills directly in your work. Let's get started. Let's start with a simple question. What is demand planning? At its core, demand planning is the process of estimating future customer demand for product or service, so the businesses can make the right decisions today. Let me explain this with the help of an example. Imagine you're in the business of selling cookies, and let's assume it takes 4 weeks to produce those cookies. Now, if you want to meet customer demand successfully, you cannot wait until the orders arrive from the customers. You need to know today itself how many cookies are customers likely to need 4 weeks from now. If you have that visibility, you can procure the raw materials in advance, you can set up the production schedules, align people and resources, and ensure that in 4 weeks' time, you have the right quantity of cookies produced and ready to be shipped. This process by which businesses estimate the future demand is called demand planning. The demand planning function produces a forecast for the future demand of products and services, and based on this forecast, businesses can take some very important decisions today, such as how much to produce, how much to buy, how much inventory to hold, and how much capacity is needed across the supply chain. The key idea here is that demand planning exists because demand and supply do not naturally align on their own. Customers usually behave in an unpredictable way. They may want products at different times in different quantities with different variants, and sometimes on a very little notice. Supply and production, on the other hand, need discipline, structure, and planning. For example, factories need lead time to produce the products, suppliers need some forecast about how much raw material are we going to be buying from them, warehouses need a space, and so on. So demand planning sits right in the middle between the customers and the supply side of the business. Its role is to translate the uncertain customer demand into actionable numbers that the production, procurement, and various other functions of the business can work with. So if I had to summarize demand planning in one line, it would be this: that demand planning reduces uncertainty so the business can plan with confidence. Demand planning does not work in isolation. In fact, it's one of the most cross-functional roles in the organization. Let's take a quick look at some of the key stakeholders that demand planning works closely with. Sales team provides market intelligence. They have information about how many promotions are they going to do in the market, customer wins and losses, pipeline changes, and so on. Demand planners use the information from the sales team to adjust the demand forecast accordingly. But at the same time, they also use data and history to challenge the numbers coming from the sales department. Marketing can influence demand through marketing campaigns, advertisements, pricing changes, product launches, and many other activities. If marketing plans are not reflected in the demand forecast, forecasts could be at a risk of being wrong. Supply planning is one of the most important stakeholders of demand planning. Supply planning team uses the demand forecast to decide how much raw materials they should buy, how should they structure their production plans, how to manage the capacity constraints, how much inventory to hold, and so on. If demand planning overestimates the demand, which means that the actual sales turn out to be lesser than the forecast, then inventory can pile up, which can lead to inventory write-offs. If demand planning underestimates the demand, then service levels can suffer because business will not be able to fulfill the customer orders. Finance uses the demand forecast for revenue forecasting, budgeting, and cash flow planning. That is why demand planning and finance are very tightly linked. They often work off the same numbers. So think of demand planning as a coordination role. It aligns assumption across different teams into one agreed view of future. Now let's talk about the roles and responsibilities of demand planning. Because the job is not just to build forecasts, there are some important aspects to it. Here are some of the most important responsibilities. First, the demand planning team creates and maintains the demand forecast. This is one of the most important roles. Demand planners use the historical data, apply statistical forecasting techniques, adjust for seasonality, trends, and promotions, and ultimately, as a result of these steps, they come up with a demand forecast by product, location, or customer. Secondly, demand planners also manage the forecast accuracy and bias. They continuously track forecast error, biases, and forecast changes over time. The goal is not perfection. The goal is to improve forecasting process continuously. Thirdly, they facilitate the alignment discussions. Demand planners run and manage the forecast review meetings. Usually, these are also called demand review meetings. These are the meetings where sales teams give their inputs, marketing teams share their plans, and supply team flags the production constraints. The demand planner's role is to bring structured data and objectivity to these discussions. Lastly, but most importantly, demand planners act as a single source of truth. Once the demand forecast has been agreed, all the functions in the organization use it. This makes demand planning a high impact and high responsibility role. So to summarize, demand planning exists to reduce uncertainty. It sits at the center of multiple functions, and its core job is to turn data, assumptions, and collaboration into a reliable forecast. In the next lessons, we'll deep dive to understand what forecast is and why having a forecast is important for a business. In the previous lesson, we talked about demand planning and why the function exists. Now let's zoom in on the most important output of demand planning, that is the forecast. So what exactly is a forecast? At its core, a forecast is an informed estimate of the future demand of products or services. It is based on historical data, patterns, assumptions, and the best information available at a given point in time. A forecast is not a fact, it's a best estimate, and this distinction is extremely important. A forecast tells a business, based on what we know today, this is what the demand is likely to look like in future. This allows teams to plan ahead even though the future is uncertain. Now let's be very clear about what a forecast is not. A forecast is not a sales target, it's not a commitment, and it's never a guarantee. In real organizations, many problems arise because forecasts are treated as promises rather than estimates. The reality is simple. All forecasts are wrong because actual numbers will never be exactly the same as the forecast. Sometimes they are way off or sometimes they are slightly off, but they are never exactly the same as was in the forecast. And that's not a failure. That's just the nature of forecasting. Actual demand is influenced by customer behavior, market conditions, competition, promotions, and many other factors that cannot be predicted perfectly. So if forecasts are always wrong, why do we even bother creating them? Because the purpose of forecasting is not to be perfectly accurate. The purpose of forecasting is to help the business make better decisions than just random guessing in the air. A good forecast reduces uncertainty, creates alignment across the teams, and allows the business to plan production, inventory, and capacity in advance. Even an imperfect forecast is far more useful than no forecast at all. This is why forecasts are so critical. They act as a common planning language across the organizations, used by supply planning, operations, finance, and leadership teams. In the rest of this course, we will focus on how forecasts are built, how they are evaluated, and how they are improved over time. But the mindset we should keep throughout this course is that a forecast is an estimate, not a promise, and its value lies in better decisions, not perfection. In the previous lesson, we clarified what a forecast really is. It's an estimate and not a promise. Now let's build on that idea and introduce an important distinction. In most organizations, you will come across two types of forecast. the macro forecast and the micro forecast. And it's important to understand the difference between the two and why they both exist. Let's take a simple example. Assume you work for a company that sells two product categories, cookies and chocolates. Within each category, you sell 3 SKUs. An SKU is a stock keeping unit. Simply put, it means a unique product variant. For example, 200-gram vanilla cookie pack or 500-gram chocolate cookie pack. Now assume you have been asked to prepare a sales forecast for the year 2026. There are broadly 2 ways in which you could approach this. In the first approach, you forecast demand on a higher or an aggregated level. For example, you will say that the cookies are going to sell 200 units each quarter and the chocolates are going to sell 100 units for each quarter. This is the first approach. In the second approach, you forecast demand at a much more granular and detailed level. For example, by SKU, by month, and possibly by location or channel. The first approach is what we call the macro forecast. This is a forecast that has numbers on a higher or an aggregated level, for example, volumes by categories and on a quarter level. The second approach is the micro forecast. It's a more detailed view with numbers for each SKU and each period. Now, the obvious question is, why do these 2 forecasts exist in the same organization? The answer is because they serve different purposes and are created in different ways. Macro forecasts are usually formed by looking at the external environment in which the business operates. For example, population growth, inflation rates, economic outlook, technological and social trends. For example, if the population of a country is expected to grow by 5%, the leadership and marketing team of the company might expect the total company sales to grow by a similar magnitude. This is a macro-level forecast. Macro forecasts are useful for directional planning, strategic discussions, and leadership communication. They help answer questions like where the business is heading and how does the external environment in which the business operates is looking like. However, macro forecasts are way too aggregated to run the day-to-day operations of the business. For example, if I tell my plant manager that the total cookie sales will be 200 units in Q2 of next year, then that information is not sufficient enough for them to create a production plan. Plants do not just produce total categories or total cookies. They produce specific products in specific quantities at specific times. For example, instead of knowing the total cookie sales will be 200 units in Q2 of next year, they need to know how much exact amount of 200-gram vanilla cookie packs are needed in the month of April so they can do the production accordingly. This is where micro forecasts come in. A micro forecast breaks down the demand into details such as by product or SKU, by location or warehouse, by customer or channel, by month, by week, or in some cases even by day. This level of detail is critical for operational execution. Production planners don't just produce total company sales or total cookies, they produce individual SKUs. So they need to know how much of each SKU needs to be produced so they can set up their production plans. That's why demand planning typically focuses on micro-level forecasting. To build these forecasts, demand planning collects input from sales, marketing, supply, and other functions of the business and converts them into a detailed demand view. Now, the next question that comes to mind is that will having 2 different sets of forecasts will create confusion or clashes in the organization? Well, if organizations have the right discipline and forecasting processes, that will not be the case. In well-run organizations, macro and micro forecasts complement and validate each other. Let's assume the following scenario. A marketing team forecasts that the cookie sales should grow by 10% because the population of the country is expected to grow by 10% next year. This is the macro forecast. The micro forecast set up by demand planning shows only 7% growth in cookies. This does not mean that micro forecast is wrong. There could be some very good reasons why micro forecast is lower than the macro forecast. For example, there could be some products that are being discontinued. Have we lost some customers? Are there production capacity constraints due to which we are not able to produce enough even though the demand is there? So the difference between a macro and a micro forecast will trigger a healthy business discussion. The goal is not to force numbers to match between the macro and the micro forecast, but to understand the business reasons behind the gap. This is why demand planning plays such a crucial and central role. Their job is not just mathematical forecasting. Their job is to ensure that micro-forecasts are realistic and executable, they make sense when viewed against the macro outlook, and have a clear business logic behind them. To summarize, macro forecasts are created based on external macroeconomic factors. Micro forecasts are driven by inputs from internal business functions. Macro forecasts are highly aggregated, for example, category-level forecast by quarter. Micro forecasts are granular and more detailed, for example, SKU-level forecast by month. Macro forecasts are typically created once or twice a year. Micro forecasts are created more frequently, most commonly on a monthly basis. We're going to explore this point further in the lecture on forecast governance. Macro forecasts are usually developed by marketing or the strategy teams. Micro forecasts are owned and managed by demand planning teams. Macro forecasts are used by leadership team to understand the overall direction of the business and its environment, whereas the users of micro forecast are usually the operational teams. Their purpose is to guide day-to-day execution and operational decision-making. Since this is a course on demand planning, our focus will be on micro forecasting. In the next lessons, we'll start looking at how micro forecasts are actually built and explore some commonly used forecasting techniques. So far, we have talked about what demand planning is, what a forecast really represents, and two types of forecast, that is macro forecast and micro forecast, which you will usually encounter in organizations. Now let's move into the next big topic, that is forecasting techniques. A forecasting technique is simply a method used to estimate future demand of products or services based on available information. There's no single best forecasting technique. In practice, different techniques exist because different situations require different approaches. Some techniques work well when the demand is stable, others are better suited when demand is volatile. Some require large amounts of historical data, whereas others work even with very limited history. In the next few lessons, we're going to cover a range of forecasting techniques, from statistical methods to simple rule-based approaches. For each technique, we're going to understand the logic behind the technique, discuss when it makes sense to use that technique, and implement it step by step in Microsoft Excel. We're going to start with techniques that focus on patterns in historical data, such as the moving averages and time series methods. Then we're going to move into regression-based techniques, where demand is linked to one or more influencing factors like price or promotions. Finally, we're going to look at simple but widely used approaches such as extrapolation and growth-based forecasting. The goal is to help you understand how different forecasting techniques work, what assumptions they rely on, and when each technique makes sense in demand planning context. We're also going to learn how to implement each forecasting technique in Microsoft Excel, and this is quite important because later on in the course, you're going to be building an automated forecasting model in Excel, where you input historical actual sales data, select forecasting assumptions or techniques for different SKUs, and the model should automatically generate a 12-month rolling forecast. By the end of this section, you won't just understand the forecasting techniques, you'll know how to apply them in Excel and which technique should be selected in which situation. Let's start off with the first technique, that is simple moving average. Let's start with one of the most commonly used forecasting techniques, the simple moving average. A simple moving average forecasts the future demand by averaging the demand from the recent past. Let's look at a simple example. Assume you have data for the last 12 months of actual demand of 10 products. You want to forecast the demand for the month of January 2026. If we use a 3-month moving average, we will take the average of actual demand from the last 3 months, that is October to December. For example, in case of SKU001, the forecasted demand for the month of January 2026 will be 101 units, because we will take the average of October, November, and December, which is 101, 100, and 102. Moving averages can be calculated over different ranges. For example, 3-month moving average, 6-month moving average, or 12-month moving average. The logic stays the same. Only the number of periods included in the average change. A 3-month moving average uses the last 3 months of data, whereas 12-month moving average uses the last 12 months of data. The choice of range has a direct impact on how the forecast behaves. Using a shorter range for moving average will produce a responsive or a volatile forecast, whereas using a longer range of average will produce a more stable forecast. This brings us to an important concept, that is forecast responsiveness versus stability. Responsiveness refers to the ability of a forecast to quickly adjust to real changes in demand patterns. In other words, it refers to how fast your forecast responds to genuine changes in demand. Stability, on the other hand, refers to the ability of a forecast to stay consistent over time. In other words, how well your forecast avoids overreacting to random noise in demand. Ideally, you would want to strike a fine balance between the two. An over-responsive forecast will lead to high volatility, which can ultimately give confusing signals to supply and production teams. An overly stable forecast, on the other hand, is good for supply planning teams. However, it might not appropriately take into account genuine changes in demand. A shorter moving average, like a 3-month average, reacts quickly to recent demand changes, and that's why it's more responsive. A longer moving average, like a 12-month average, reacts slowly to demand changes and is more stable. Let's understand this with the help of an example. Assume this product had fairly stable demand of 100 units per month for a very long time. But in the last 3 months, the demand suddenly increased. In October, it was 150 units, November 160 units, and December 170 units. Now we need to forecast the demand for the month of January 2026. If we use a 3-month moving average, it results in a forecast of around 160 units for the month of January. And even for the months after, the forecast will be in the range of 160 units or so. You can see that the forecast has responded quickly to recent demand changes because the moving average is heavily influenced by recent demand. Now let's take a look at 12-month moving average. Here the forecast includes 9 months of demand at around 100 units and only 3 months of higher demand. So even though the forecast for the month of January does increase with the 12-month moving average as well, but it increases much more gradually. Instead of jumping to 160 right away, the 12-month moving average might move to something in the range of around 115 to 120 units. This clearly shows the trade-off. A shorter moving average reacts quickly to demand changes, and it's more responsive. A longer moving average smooths out sudden changes and is more stable. The range of average needs to be selected carefully because there are pros and cons on both sides. If recent spike in demand is temporary or driven by a one-off event, then using a short-range moving average might overreact to these demand spikes and might result in an over-forecasted demand. On the other hand, if the recent spike in demand is of a permanent nature and business expects it to continue, then using a long-range moving average might be too slow to react to these genuine demand shifts. This is why choosing the range of moving average is not a technical decision or a mathematical decision. It's a business decision. The right choice depends upon the nature of the product, the life cycle of the product, and how quickly the business wants the forecast to react. Now that we understand the logic behind simple moving averages, let's move to the practical side. In the next part of this lesson, I'll show you how to implement moving average forecast in Excel step by step. Here, I have got actual demand data for 10 SKUs for 12 months from January 2025 to December 2025. In real business scenarios, data sets are typically much larger. For now, I'm using a simplified data set so we can clearly focus on the core idea behind moving averages without getting tangled with unnecessary data complexity. We want to calculate forecast demand for the next 12 months, that is from January 2026 to December 2026. If we want to calculate it using 3-month moving average, we can do so by simply using an average formula. So I'll write in an average formula, and then I'll select the last 3 months, close the formula, and that's all. Now I'm going to copy the formula by pressing Ctrl+C on the keyboard, and then I will paste the formula in the rest of the cells. So the moving average for the month of January will be calculated as an average of actual demand from October to December. February will be the average from November to January, and March will be the average from December to February, and so on. One important point to be mindful of is how you treat months with zero actual sales. If a month shows zero volume, you need to decide whether zero represents a true demand or it's a data anomaly. For example, let's assume in SQ001, in the month of October, we had zero sales. If I put zero over here, you will see that the average that gets calculated for the month of January drops down. But before including the value in moving average, you should ask why the sales were zero. If sales were zero due to a non-recurring issue, for example, if the sales for the month of October were zero because we were out of stock on this particular product in the month of October, then this means that the demand still existed, but the business could not supply because of the stockout issues. In such cases, including zero in the average would artificially pull the forecast downwards and distort the outlook. A better approach is to exclude that month from the calculation altogether. In Excel, the simplest way to do this is to leave the cell blank instead of zero. For example, here, instead of zero, if I leave the cell blank, then you will see that in the average calculation, the formula is going to calculate the average of November and December only. The average function in Excel ignores the blank cells, so the month of October will not be included in the moving average calculation. I will do Ctrl-Z to go back to the original position. If we want to calculate 12-month moving average, we can simply drag the range of average formula to 12 months. For example, here, I'll drag the range to last 12 months. Then just like before, I'm going to copy this formula and drag it to other months and other products. Now the forecast for all the months is getting calculated using 12-month moving average. We just saw that if you want to change the range of moving average, we can simply change the range that goes inside the average formula. But in real scenarios, you often don't want to use the same moving average length for every product. For example, you may want to use 3-month moving average for some SKUs, a 6-month moving average for others, and 12-month moving average for the rest of the portfolio. And when you're working with many SKUs, changing the ranges of the average formula for each and every SKU one by one could be quite tedious and time-consuming. This is where some level of automation in Excel can become very powerful. Instead of hard-coding the moving average range inside the formula, we can design the model so that the range is controlled by an input cell. That way, when you change the input, say from 3 months to 6 months, the moving average calculation automatically adjusts. Let me show you what it looks like. Here in this model, on the right-hand side in column AA, I have an input cell where we need to define the moving average range. If I put 3 over here, the calculation of the moving average adjusts to 3-month moving average. If I put 6, the calculation automatically adjusts to a 6-month moving average. If I put 12, it will show us 12-month moving average, and so on. To build this kind of flexibility in automation, we need to first learn an important Excel function, and that function is called the index function. That's what we're going to learn in the next lesson. Before we jump into the formula, let's first understand what the index function does. Think of index function as a pointer. You give it a range of cells and then define the position within the range from which you want to retrieve the value, and index function is going to get that value for you. Let's say I have this range of cells over here. From this range of cells, I want to get the value which is in the green highlighted cell. One option to do that is to just simply write an equal to sign and then write the address of the cell from which I want to get the value. The address of this cell is cell B7. It's in column B, row number 7. I'll put that in and I'll get the value. Likewise, if I want to get the value from this particular cell, then I will put this cell's reference, which is M7. If I want to get all the values between cell B7 and cell M7, that is 2 cell addresses, then I can write the address of the first cell, then put a semicolon, and then write the address of the second cell, which is M7. If I press enter, I will get all the values that exist between these 2 cell addresses. So all in all, we learned that if we want to get a particular value, we can just write an equal to sign and then give the address of the cell from which we want to get the value. However, that's not the only way. We can also use the index function. In index function, I will first select the entire range of cells that I want to play with. Then I will define the position of the cell from which I want to retrieve the value in terms of the rows and the columns in which that particular cell sits within the given range. For example, if I want to get the value of this particular cell, then I will define which row number and which column number this cell is sitting in the given range. In this particular range, this cell is at row number 5. So in the second argument, which you can see is row number, I'm going to put in 5, and it sits in the first column of the given range. So I'll put 1 in the column number. When I close the bracket, I'll get that value. Likewise, if I want to get this value, I will put the coordinates in terms of the row number and column number of this particular cell. This cell is in row number 5 and column number 12. So in column number, I'm going to give 12, and it will give us this value. Now the question is, why would you want to use an index function when you can just simply write the address of the cell and get the value from it? The reason is that index function can help you make your formulas dynamic. For example, here I have hard-coded the values of the row and the column numbers, but that's not necessary. I can make them dynamic as well. So for example, here I can create a column which has the row number. This one will be the column number. And instead of hard coding the row number and column number inside the formula, I can put the row number here and the column number here. And instead of hard coding it, I will give references to these two cells. Row number is in cell R7 and column number is over here. Now, instead of getting the value from this cell, if I want to get the value from this cell, all I will do is change the column number to 1, and the value will update automatically. So I don't need to manually drag the formula here and there. I can control the reference that this particular function is referring to by changing the inputs in these two cells. An important thing to remember about index function is that on the outset, it is returning us the value that is inside the cell that we are pointing towards, but internally, Excel treats this formula or this function as a reference to the address of the cell that we are pointing towards. For example, internally, Excel evaluates it as a reference to cell B7. Likewise, if I write another formula here, and in this one, I will give row number 5, column number 12, then in this particular formula, internally, Excel is evaluating it as a reference to cell address M7. Now, we already discussed about it, that if I write two cell references, let's say I write reference to cell B7, and then I write reference to cell M7, and separate these two cell references with a semicolon, we will get all the values that exist between those two cell references. So likewise, in the index function, we already said that this function is evaluating internally as a reference to cell B7, and this function is evaluating internally as a reference to cell M7. So if I write these two index functions in the same formula and segregate them with a semicolon sign, then we should get values of all the cells between these two references. Let's try it out. First, I'm going to write this formula here. It's evaluating as a reference to cell B7. And this index formula, as we already talked about, is evaluating as a reference to cell M7. I'm going to take this formula, write a semicolon, enter the second index formula, and if I click on enter, then I will get all the values between these two cell references. The first part of this formula evaluates to cell B7. The second part of this formula evaluates to cell M7. And that's why we are now getting all the values between these two ranges. The first part of the formula, as you can see, is controlled by these input cells. If I change anything in this input cell, the reference to which this part of the formula is referring to will change. For example, let's say instead of referring to cell B7, I want the first part of the formula to refer to cell K7. This means I will need to select column number 10. If I select column number 10, then you will see that it will only return the last 3 values. Likewise, if I select column number 11, it will only return 2 values. If I select column number 6, it will return the last 7 values. Also, let's say now I want to calculate the average of all of these values that are coming out as a result of this function. Then I can just write an average formula and wrap the entire formula inside an average function. It will give me the average of all the values. Now that we understand the index function, we can go and set up the automation that we were talking about. Here in this cell, I will first write in the index function, select the last 12 months. I will select the first row and the 12th column. This will give me reference to cell M7. If I drag this formula rightwards, it will always give me reference to the last month just before the month in which the formula is living. Now, let's say I want to return all the 12 months that are in the range. So I will write another index formula, segregate the two with a semicolon, and in the first part of the index formula, I will give reference to column number 1. Now, if I wrap it up inside the average formula, technically speaking, I'm getting 12-month average. But let's not wrap it right now. I'll do Ctrl-Z, go back to the original position. Let's say if you want to find 3-month moving average, then I need the formula to return these 3 cells. This means that in the first index function, I will give column number 10. Now, if I wrap it inside the average function, it will give us 3-month average. So basically, by changing the column reference of this first index function, we're able to change length of range that comes as a result. So I can link this particular column reference to the input of the moving average range. We want to set it up in a way that if the user puts 3-month moving average, the answer over here becomes 10. If someone puts 6-month moving average, we would want the column number to become 7, and so on. So one way to do that is we can put 12 over here, minus 6. 12 minus 6 will be 6 only. We want to return 7, so I'm going to put 1 as well. And that's it. Now it's giving us the values that are there in the last 6 months of the selected range. If I put 3 over here, it's going to give us the last 3 values in the selected range. Now I can wrap it up inside the average formula. And there we go. I will copy it in the rest of the cells. I just need to freeze the reference to this particular cell so that it doesn't move. Just to test things out, let's take an example of SQ number 3. Right now, this number is calculated as an average of the last 12 months. As you can see, the average is 117.5. We are getting 117.5 here as well. If I select 3 months, it gives us 170. The average of these 3 months is 170, and that is what we're getting here. If I select 6 months, it's going to give us the average of the last 6 months. Simple moving averages work best under a few specific conditions. First, when there is no strong trend or seasonality in the demand. For example, imagine a product that normally sells around 20 units per month, but in the months of June and July, the demand suddenly jumps to 100 units per month. This is a seasonal pattern. Maybe it's a summer product, for example, an ice cream that sells a lot in the months of June and July, but not as much in the rest of the months. If we apply a simple moving average here, those seasonal peaks get averaged out with the rest of the months. And as a result, the forecast becomes flattened. The seasonality disappears and the forecast no longer reflects the reality. So simple moving averages are not suitable when the demand has a strong or recurring seasonal patterns. Secondly, simple moving averages work really well when recent history is a good indicator of the near-term future demand. This assumes that the prices are not changing significantly promotion strategies are stable and are expected to stay stable in the near future, and there are no major business or market shifts planned. For example, if you're planning to reduce prices or launch aggressive promotions in the upcoming months, then the demand may increase naturally. But a simple moving average technique cannot anticipate that change. It will only reflect what has already happened in the recent past. So at its core, the simple moving average makes one key assumption. That is, the future will look broadly similar to the recent past. And because of this assumption, moving averages are easy to understand, easy to explain to stakeholders, and very commonly used in practice. But the same assumption is also what defines their limitations. In the last lecture, we learned about simple moving averages. We saw that moving averages can work really well when demand is fairly stable, and recent history is a good indicator of what might happen next. But moving averages have an important limitation. They don't explicitly handle seasonality. For example, have a look at SQ007. The demand spikes in the month of June and July every year. A simple moving average tends to smooth out those peaks, which can lead to a forecast that misses the seasonal pattern. So what we need is a technique that can do two things. First is capture the underlying trend over time, which to a large extent, simple moving average is doing. But also in addition, it should detect and project the seasonality. This brings us to the time series forecasting technique. Time series forecasting is about identifying patterns in the historical demand and projecting those patterns into the future. Now, how does time series actually work? At a high level, it asks how the demand has behaved over time and what parts of that behavior are likely to repeat. Let's think about it step by step. First, the time series forecasting looks at the historical demand and establishes what a demand looks like on an average. This component is called the baseline level, or the baseline component. Next, it checks whether the demand is generally on an increasing trend, decreasing trend, or is it relatively stable. That becomes the trend component. Then it looks for repeating patterns like higher demand every summer or lower demand at the start of the year. That becomes the seasonality component. Once these pieces are identified, the forecast is generated by combining these three components together. So unlike a moving average, which can flatten out the patterns, time series forecasting aims to preserve the structure in the historical data. Let's have a look at how we can implement time series forecasting in Excel. To apply time series methods effectively, we need a longer history of data. Typically, that means we need at least 24 to 36 months of historical demand data. So here, I've extended the data set and included 36 months of history for 6 different SKUs. Also, I have plotted the historical demand data on a chart at the bottom so we can observe the patterns. For example, the chart currently shows the pattern for SQ002, and we can see that SQ2 is on an increasing trend, SQ003 is on a declining trend. In SQ004, we have a seasonality pattern where the demand spikes in the month of June and July. SQ005 is also a seasonal SKU, with the demand spiking in the months of November and December every year. SQ006 is pretty flattish SKU. There was just a bit of a bump in the month of July. And SQ001 shows an uneven forecast. Once we calculate the forecast using time series technique, we're again going to have a look at how the forecast has been shaped for the future months. There is a built-in function in Excel that basically applies the time series logic internally. That function is called forecast.ets, so we're going to use that. I'll write forecast.ets. The function has 3 mandatory arguments. The first argument is the target date for which we want to generate the forecast. We want to generate the forecast for January 2026, so I'm going to select that. And I'm also going to freeze the row reference, so the formula can move around easily along the columns, but it stays frozen along the rows. In the second argument, we need to provide the historical values. So I will select this. Again, I will freeze the references to the columns, but keep the rows dynamic. And in the third argument, we need to provide the timeline, the historical timeline. So here, I'm going to select all the dates for which we have the data. And this time, I'm going to completely freeze the reference to the date range. The fourth argument is an optional one, but it's important for our case. This indicates seasonality. Our data has 12-month seasonality, so I'm going to key in 12. I'll close the formula, press enter, and then I'm going to drag the formula to the rest of the cells. Now let's have a look at how the forecast has been shaped out. For SQ002, for the forecast months as well, there is an increasing trend. For SQ003, which was historically showing a declining trend, the forecast has continued on that trend. In SQ004, we can see that the seasonality has been predicted quite accurately in the month of June and July. This is the point that the simple moving average was missing. If we look at SQ005, November and December months have seasonality component in there. And for SQ006, there is a bit of an increasing trend in the forecast, so that has been captured properly. So all in all, time series forecasting is especially useful when demand shows a clear trend and it follows a repeating seasonal patterns. And also, the past behavior provides a meaningful insight into future demand. Unlike simple moving averages, time series methods can preserve seasonality, and this makes them a very common technique in demand planning and forecasting systems. It's important to understand that time series methods are not completely different from moving averages. In fact, many time series techniques use moving averages internally or apply smoothing logic in a more structured way. So you can think of time series forecasting as an extension of the smoothing techniques with added intelligence around trend and seasonality. Just like any technique, time series forecasting also has some limitations and assumptions. It assumes that the historical patterns will continue and that the trend and seasonality observed in the past will persist into the future. If the business environment changes significantly, for example due to pricing changes, promotions, or market disruptions, time series models alone may not be sufficient and it will not be able to incorporate these impacts into the forecast. This is why time series forecasting is often combined with business judgment, inputs from the sales and marketing teams, and scenario-based adjustments. To summarize, moving averages smooth the demand and ignore the seasonal patterns. Time series forecasting decomposes the demand into patterns like baseline, trend, and seasonality, and forecast the future demand using these patterns. So far, we have looked at forecasting techniques that are driven entirely by historical demand. Simple moving averages smooth out the past demand. Time series forecasting detects patterns like trend and seasonality, again based on historical data, and project that in future. And that's an important limitation to remember. Time series methods assume that the forces shaping the demand in the past will remain broadly similar in future as well. For example, if the demand has been trending upward for the last 3 years, time series will typically project that trend forward as well. But what if business conditions are about to change? Let's say that in the past we kept our prices relatively lower, but the next year we are planning to take a significant price increase. Will the demand from the past still follow the same trend? Most probably not, because an increase in price will have at least some impact on the shape of the demand. Time series alone cannot answer that because it doesn't see the future pricing decisions. It only sees the demand pattern from the historical data and projects it into future. So when future demand is likely to change due to business actions like pricing, promotions, marketing strategy, we need a different forecasting approach. That brings us to linear regression. Linear regression is a statistical forecasting technique where demand is explained using a business driver rather than the time alone. Instead of asking how has the demand behaved over time in the past, regression asks what factors are driving the demand and how strong is the relationship between the demand and those factors. These factors are often called drivers. Common demand drivers include prices, promotion spends, marketing spend, distribution reach, number of customers reached, and sometimes broader economic indicators. Now let's take a simple example. Assume we want to understand how demand changes with price. Here I have a chart showing historical demand and historical price for a particular product. In many categories, we typically observe a pattern between demand and price as follows: that when price goes up, the demand tends to go down, and when price drops, demand tends to increase. Linear regression helps us quantify that relationship. For example, it might estimate something like a 1% decrease in price leads to a 2% increase in demand, or whatever the relationship your data actually shows. Once we estimate this relationship, we can forecast demand under different future assumptions. For example, what happens to demand if we increase the price by 5%? Or what if we run a promotion next quarter? This is something time series methods cannot do on their own. When is linear regression useful? Linear regression works best when you can identify a meaningful driver that has an impact on the demand and you have historical data for both demand as well as for that driver. It's especially useful for pricing decisions, promotion planning, scenario analysis, and understanding demand sensitivity. To summarize, time series explains demand using patterns over time. Linear regression explains demand using business drivers and other economic indicators. In demand planning, both are important forecasting techniques. And as a good demand planner, you should have a strong grip on both the techniques. In the next lecture, we'll implement linear regression model in Microsoft Excel step by step. See you there. In this lesson, we're going to learn how to implement linear regression in Excel. I have the historical data for 4 products. For each product, I have actual demand for the last 6 months and the prices at which these products were sold during those months. I also have the planned prices for the next 6 months over here. Our objective is simple. Using the relationship between historical price and historical demand, we want to estimate what demand might look like for the next coming 6 months. And in other words, we're trying to answer a practical business question, that is, what the demand will be if I sell these products at these forecasted prices. To achieve this, we'll need to do 2 things. First of all, we'll need to quantify the relationship between the historical price and historical demand. And once we've done that, we'll use that relationship to generate a demand forecast for the future months. Now at this stage, some of the students might be wondering that demand is not driven by price alone. There could be some other factors like promotions, marketing spend, seasonality, weather, etc. And you're absolutely right. We'll look at multi-driver situations in upcoming lessons when we will study about multivariate regression. But for now, to build a strong foundation and to keep the mechanics clear, we're just going to focus on only one driver, and that is price. Excel provides a built-in function for linear regression, and that function is called linest. At a high level, in this function, Excel estimates 2 things. First, it estimates how much does the demand change per unit change in driver, or in this case, per unit change of price. This is called the slope or coefficient. Second, it estimates what is the baseline level of demand, or what the demand is going to be when the value of driver is 0. This is called baseline or intercept. So when we use the linest function, we get 2 key outputs. The slope, which measures the first point, that is, by how much does the demand fluctuate due to change in price, and the intercept, which represents the baseline demand. Once we have these 2 values, we can estimate the demand for future months using a simple equation. Here in this equation, yn is the demand in period n, which we're going to find out. A is the intercept or baseline demand, which we're going to get from the linest function. B is the slope or coefficient. We're also going to get this as well from the linest function. And x is the price in period n, which we're going to get from our price forecast. Before we use the linest function, there's one important concept we need to be clear about. That is the dependent and independent variables. The variable that we are trying to predict, and in this case that is demand, is called the dependent variable, also referred to as the y variable. The variable that drives or explains the changes in demand, and in this case that is price, is called the independent variable or the x variable. When we pass in the historical values of x and y variables into the linest function, it returns us the slope and baseline values. Using these slope and baseline values in the linear regression equation, along with the forecasted future values of the x variable, we can forecast the future values of the y variable. Let's do a walkthrough of how we can use linest function in practice. Here in these two columns, I want to get the values of slope and baseline. So here, I'm going to use the linest function. First of all, I need to provide all the values of the y variables. So I'm going to select the y values of SK1. And then I need to provide the x variable values for SK1. X variable in our case is price, so I'm going to provide in that. Then I will close the formula, and we will get the values for slope and baseline. Now I can drag this formula down. So for all the four products, we now have the values of slope and baseline. We can use these values in the equation of regression which we just saw to forecast the future demand. So I'm going to take baseline plus coefficient multiplied by the forecasted price. Let's freeze the references. And there we go. We have the forecast for the future periods. At the bottom here, I have a chart that visualizes the demand trend. The numbers for the first 6 months from July 2026 to December 2026 are actual numbers. The next 6 months from January 2026 to June 2026 are forecast numbers which we have calculated using linear regression. Right now the chart is showing the values of SQ002, but if we want we can change it as well. For example, if I put in any other SQ here, I'll put in SQ003, then the chart is going to show me the values of SQ003. For now, let's look at SQ002. As you can see for this SKU, since we are planning to take price increases in future months, the demand is going downwards. But if we change our plan and decide to keep prices lower, you will notice that the demand is going to go upwards. For example, if we decide to sell this product at a price of 8.2, the forecast for the future months is going to change automatically. So that way, linear regression not only forecasts the future demand based on a driver or price, but it can also help in scenario analyses and decision making. In the previous lesson, we implemented a linear regression model in Excel using sales volume as the dependent variable and price as the independent variable. In that example, the driver, which was price, was a numerical value. But in practice, that might not always be the case. Sometimes the factor influencing the demand might be categorical in nature and not numeric. Let's look at a common example. Imagine your business runs promotion activities such as placing a promotion display in a retail store. When the promotion display is active, the sales typically increase. Now assume you have historical monthly sales data, information on whether a secondary display or a promotion display was active in each month, and a plan for whether these displays will be used in future months or not. Based on this, you want to forecast future demand. In this case, sales volume is still the dependent variable, but the independent variable is not a price, it's promotion, which is categorical, with values like yes or no for each month. Regression models, however, work with numbers only, not text. So the first step is to convert this categorical variable into a numerical format. A simple and a very common approach is to use binary coding. For months where there is no promotion display, we assign a value of 0. And for the months where promotion display is active or is going to be active, we assign a value of 1. Once we do this, the promotion variable becomes numeric in nature, and then we can run the linear regression in a normal way between sales volume and promotion activity. Let's see how it's done in Excel. Here, I'm using the same Excel file which we developed in the last lesson. I have actual demand numbers by month, and I have data about whether in each of the actual months we had a promotion display or not. 1 indicates that we had a promotion display active, whereas 0 means that we did not have promotion active in that month. Also, for future months, we have a plan here, which indicates whether we're going to have a promotion active in the upcoming months or not. The Linus formula is calculating the slope and intercept here on the right, as usual. In the columns for future demand, we are calculating demand forecast using the regression equation, which we learned in the last lesson. From the trend chart, we can see that in the months where we have promotions, the demand tends to go up, and in months where there is no promotion, the demand stays low. So the regression output tells us how much sales typically increase when a promotion is active compared to when it's not. And this allows us to explicitly reflect future promotion plans directly in the demand forecast. Next thought we might have in mind is that demand is not only influenced by prices alone or promotion alone, it's influenced by both factors simultaneously. So how do we model a demand that takes into account both of these drivers at the same time? This can be handled via multivariate regression, which incorporates the impact of multiple drivers at the same time. We're going to study about it in the upcoming lessons. We've learned how to run linear regression in Excel. Before moving on, let's pause and answer an important question. Should you be using regression at all? For example, in the last exercise, we regressed the demand volumes on price. But before using price as a driver, we need to ask an important question. Is price actually a good predictor of demand for this particular product? In some categories, the answer is clearly a yes. For price-sensitive products like clothing, sweets, general food products, changes in price often lead to noticeable changes in demand. If you look at this chart, you'll see a clear pattern. When price goes down, volume goes up, and vice versa. In this case, price has a strong explanatory power. But that's not true for every product. Some products are less price sensitive or even price insensitive. Think about categories like gas or water. These are necessities, so people will continue to buy them even if the prices change. If you look at this chart, you will notice that demand remains relatively stable even when the prices fluctuate. In such cases, regressing demand on price may not be very useful because the strength of relationship between demand and price is quite weak. So the key point is, for some products, regression on price makes a lot of sense. For others, it does not. But when you're dealing with lots of SKUs or products, you don't want to rely on visual inspection or intuition. You need a mathematical way to quickly assess which regression models are strong and which ones are weak. One commonly used measure to solve this problem is called R-square. R-square is a statistical value that tells us how much of the variation in demand is explained by the variation in driver, or how much of the variation in demand is explained by the linear regression model. It is expressed as a value between 0 and 1. So for example, assume I'm running a regression between demand of a product and its price, and I have an R-square value of 0.6. This means that a 60% variation in demand is explained by variation in price. This also means that the remaining 40% of the variation in demand is driven by factors not captured in the regression model, or factors other than price, for example. R-square does not tell us whether the model is right or wrong. It just tells us how much explanatory power does our model have. In this video, we're going to see how we can generate R-square values in Microsoft Excel. I'm using the same file which we created a couple of lessons back when we learned about linear regression between volume and price in Excel. In this file, we use the Linus function. You might have noticed that Linus function has a total of 4 arguments. First 2 of them are mandatory, which is the x and y variables. We only use these 2 arguments when we were creating this file. The third and fourth arguments are optional. The fourth argument is about additional regression statistics. If I put true in the fourth argument of this function, the function is going to give us other statistics in the form of a table, and one of those statistics will be R-square. Let me first delete the data from other cells. Now I'm going to put true in the fourth argument of this Linus function. And you will see that this function produces a table of stats. The value in the third row and first column of this resultant table is the R-square value. Other values are some advanced statistics which are out of the scope of this course. Now we don't want the R-square value down here. We want it in the same row right after the slope and baseline values. So I'm going to do Control-Z and rewrite the Linus function in this new column. So we now have the R-square value right here in the third row and first column of this table. By now, we know that if we want to get a particular value from a table or a range of values, we can use the index function. So I'm going to wrap up the output of the Linus function inside the index function. And then in the row number, I will put 3. And for the column number, I'm going to put in 1. Now I have the R-square value for regression between price and volume of SQ001. To get the same for other SQs, I can drag this formula down. In this example, all the regressions are quite strong. For the first 3 SQs, we have R-square of approximately 98 to 99%, which means that 98 to 99% of the variation in demand of these SQs can be explained by variation in prices. For the fourth SQ as well, the R-square is 71% or 0.71, which is also quite strong. So in this example, it makes sense to forecast the demand of these SQs using price as a driver. However, with real-world data, you might not always find such strong correlations between price and volume in your data. Let's do another exercise where we will see more realistic kind of picture. Here, I have the historical demand data for 4 products. I also have their historic price data as well as their promotion data. Since we have the data for both historic price and historic promotion values, we can run regression between volume and price first and calculate their R-squares. Next, we can run regression between volume and promotion and get their R-squares in the second column. Let's start off and first calculate the R-squares for price and demand. I will take the Linus function, put true in the fourth argument. Then I'm going to enclose it in the index function, take the third row and first column, and I will drag it down. Here I can see that for SK1 has a very strong relationship between demand and price. So 95% of the variation in demand can be explained by variation in price, but SK2 has a very weak relationship. Only 7% of the variation in demand is explained by price. And for the fourth or third SQ, approximately 37% of the variation in demand is explained by price. Now what we can do is we can also calculate the R-square for regression between promo and demand. So let's see how that looks like. So I'm going to copy the same formula, and just in this formula, I'm going to change the range which picks up the price to instead pick up the promotion. Okay, I'll just formats, and now I'm going to drag the formula down. Here you can see that SQ001 is not very sensitive to promotion. Only 4.8% of the variation in demand is explained by promotion activity. On the other hand, SQ002 is quite sensitive to promotion. Approximately 97% of the demand variation is explained by presence or absence of promotion. So if we have to make a call on what forecasting method to use, for SQ1, we should forecast using linear regression with price as the driver or the X variable. For SQ002, we should forecast using promotion as a driver, or X variable. But the tricky part is, what should we do with SQ003? 37% of variation in demand is explained by price, and approximately 40% is due to promotion. So none of these drivers is individually enough. Because let's say if I forecast using promotion as a driver, then that only explains 40% of the demand. I want to use a model that explains at least 70 to 80% of the demand fluctuation. This means we'll need to run a forecasting model that incorporates the effect of both price as well as promotion simultaneously. And this can be done via multilinear regression, which we're going to study in the upcoming lessons. In the last few lessons, we explored simple linear regression, a technique where we model a relationship between a product's demand and one particular driver, like price or promotion. Then we use that relationship to forecast future demand when the driver values are known. But in real business situations, demand is rarely influenced by one factor alone. Multiple drivers often act at the same time. We saw a hint of this with SQ003 in last lesson, where demand was partly explained by price and partly by promotion. 37% of variation in demand was explained by price and 39% was explained by promotion. So both of these drivers are important to be taken into account when forecasting the demand of SQ003. If we analyze only one driver in isolation, our forecast may be incomplete and we might miss some important insights. So we need a forecasting approach that can model more than one driver at the same time. And that's where multiple linear regression comes in. For simplicity in the rest of this course, I'll call simple linear regression SLR and multiple linear regression MLR. Conceptually, MLR is not a brand new idea. It's an extension of what you've already learned. In SLR, we estimated an intercept or a baseline demand and a slope for the driver. And then we use the SLR equation to find the forecast for future periods. In MLR, the model still estimates an intercept, but now it also estimates a coefficient for each of the driver. For example, a coefficient for price, showing how demand changes when the price changes, and a coefficient for promotion, showing how demand fluctuates depending upon whether a promotion is active or not. Once we have the intercept and the coefficient values, we calculate the forecast using this equation, where Yn is the demand of the product in period n, A is the intercept or baseline demand, B1 is the coefficient for driver 1, for example price, X1 is the price in period n, B2 is the coefficient for driver 2, for example promotion, and X2 is the promotion value in period n. And here's the key point. Each coefficient represents the impact of its driver while holding the other drivers constant. So conceptually, nothing magical is happening here. We're just extending the same regression logic to include multiple drivers in one model. To summarize, multiple linear regression explains demand using multiple drivers at once. It gives richer insight than single driver models, and it's especially useful when demand is influenced by more than one factor. In the next session, we'll bring this idea to life and implement multiple linear regression in Microsoft Excel. In this lesson, we're going to implement multiple linear regression in Microsoft Excel. We'll go through two examples. First is a simple case with one product, then we'll extend this to multiple products. Our objective is to forecast demand for this particular product, SQ001. We have historical data for demand, price, and promotion, along with forecasted values of price and promotion for this particular product. Using these, we want to generate future demand forecast using multilinear regression. In this setup, our demand is the dependent variable, or the Y variable, while price and promotion are the independent variables, or the X variables. For multilinear regression, we use the same Excel function as we did before when we were working on simple linear regression, that is the Linus function. The only difference is in the second argument of the function, that is how we pass in the values for the X variables. When we were doing simple linear regression, then in the second argument, that is the X variable, we passed in values of one X variable. With multilinear regression, we will pass in values of two X variables. As a result, the output will also expand, instead of getting just one slope and intercept value, which we got in simple linear regression, we're now going to get an intercept, and then we'll get two slope values for each x variable. And in this case, there will be one slope value for price, and then there will be another slope for promotion. So I'm going to write in slope 1 and slope 2. In fact, I will call it slope promotion slope price and baseline. Now I'm going to use the line as function. In the first argument, I will put in the historical values of the y variables. In the second argument, I need to put in the historical value of both the x variables, or the independent variables. So I'm going to select this range, which has the values for the last 6 months for both price and promotion. Once I close the bracket, the function outputs 3 values. The first value from the right side is always the baseline. The other 2 values are the slopes. We have 2 slopes here because we passed in 2 x variables. If you pass in more x variables, you will see more slopes. The first value from the left is the slope of the x variable that was passed in last. So in our example, in our range of x variables that we gave to the function, price was the first x variable, and then we had promotion. So the first value of slope from the left relates to promotion. The second value relates to price. So now we are going to apply the regression equation. So I'm going to take the baseline value plus the promotion for slope for promotion multiplied by the value of promotion plus slope for price multiply by the value of price. Now I'm going to do a bit of a freezing of the ranges. So slope will stay as it is. Now I can drag the formula, and we have the demand forecast based on both the values for promotion as well as price. Now that we understand the basic concept, let's go ahead and work with a more complicated example. I now have the same data that we used in a couple of lessons back, where we had 4 products. We have the historical demand of those 4 products, we have the historical prices of those 4 products, and we have the historical information about its promotion activities. Remember, we also talked about SQ number 003, which was partially influenced by price and partially by promotion. The R-square value for both the price as well as for promotion was in a healthy range of 37 to 39%. So basically, we need a model that can incorporate both. So I'm going to delete these columns now. I'll delete the R-square as well, just for now. And I'll delete these formulas as well. We will have slope 1, slope 2. This will be the slope for promotion. And this will be slope for price. And here we will get the baseline. Now, if I write the Linus function, I can pass in the y values very simply, but the x values are difficult to pass in a very simple way because the x values for SQ1, the prices, and the promotion are far apart. We cannot just simply select the first range of x values, that is the price, and then we select the second range of x values, that is the promotion, and separate them with a comma, because these will become 2 separate ranges altogether. So basically, we want a function where we pass in this particular first range, and then we pass in the second range, and it stacks them together. For example, if I pass in this range, and then as a second argument I pass in this range, the answer that I should get should be a combination of these two ranges stacked on top of each other. So a function that can help us do that is called vstack. I will write in the vstack function, then I will select the first range that for my function, then I'll select the second range, and once I close the bracket, you will see that the answer that this function will return will have the two selected ranges stacked on top of each other. So basically, I can use that in my linest function here. So I'll write linest, I'll give the known values of y variables, then I will use the vstack function, and inside the vstack function, I will give the values of the first x variable, then the known values of the second x variable, and that's pretty much it. I will close the function, and we will get the values for slopes and the baseline. I can drag it down. The formula that we had applied from the last exercise was only for the single linear regression, so I'm going to delete it. Now I'm going to apply the multiple linear regression formula, which is baseline plus promotion slope into value of promotion plus price slope into value of price close the bracket. Now I can write the formula. So basically we have a forecast ready based on two independent variables or x variables for all the four products. Now remember, we just said that when we were regressing SQ003 on price, it was getting 37% R-square. And when we were regressing SQ003 on promotion, it was still getting a 39% R-square. Now that we have accumulated both the drivers into one model, we should be getting a better predictability from this model. So if I want to calculate the R-square for this multilinear regression, I can do that as well. I will write in R-square. I will use the same linest function, and in the last argument, I'm going to write in true. Again, the R-square value is in the third row and first column of this range. So I'm going to write in index, and I will give reference to the third row and first column. And now I'm going to drag it down, and you will see that the R-square for SQ003 has improved significantly. And this is because when we were regressing it only using one variable, the prediction power of the model was quite low. It was either 37% or 39%, but now since our model incorporates the impact of both the variables, the strength of the forecasting model has improved significantly. Before we wrap up the regression topic, it's important to be clear about the limitations of regression models. Regression is a powerful tool, but only when used with the right expectations. The first and most important watch out when using regression is that correlation does not automatically mean causation. Just because the two variables move together in one direction does not mean that one is causing the other. For example, imagine you analyze last year's data and observe that the sales of your product increased during certain months. During those same months, number of people hired by your organization also increased. If you run a regression between your product sales and employee headcount, you might see a surprisingly strong R-square, indicating a strong correlation. But that does not necessarily mean that higher headcount leads to higher sales. The increase in sales might be responding to a third hidden factor, for example, promotion activities, pricing strategy, and so on. This is why a high R-square alone is not enough. Before trusting a regression model, you must always ask, does this relationship make business sense or not? This is why regression results should always be interpreted together with business understanding and not in isolation. The second important limitation is that regression models are built using historical data. They assume that relationships observed in the past will continue on in the future. But in real businesses, conditions don't stay constant. Suppose that historically, every 1% price decrease led to a 2% increase in demand. And your regression model captures that relationship very well. But now imagine a new low-cost competitor enters the market, or customers become more price sensitive due to economic pressure. In this new environment, the same price reduction may lead to a smaller demand increase or no increase at all, or even a decline in volume if the brand perception changes. This means that historical relationship between price and demand has now shifted. Your regression model didn't go wrong, the business reality changed. This is why regression models must be reviewed regularly, recalibrated with fresh data, and challenged when business conditions change. So far, we have covered several structured forecasting techniques: moving averages, time series analysis, and regression analysis. Before we close this section on forecasting techniques, let's briefly look at two simple but widely used forecasting approaches. Unlike the previous techniques that we studied, these are not statistical models. They are more kind of rule-based forecasting approaches. And despite their simplicity, they are very common in real-world organizations. The first technique is simple extrapolation. In this approach, we take the actual demand from the most recent period and assume that the same level will continue into future periods. For example, if demand in the latest period was 1,000 units, we assume upcoming months will also be around 1,000 units. In practice, this technique is only useful in very specific situations. It is commonly used when a product has very recently been launched and we only have 2 or 3 months of historical data, or a product is being discontinued and we expect the demand to taper off without strong patterns. In these cases, there simply isn't enough history to apply more structured techniques like moving averages, time series, or regression. This technique comes with clear limitations. It ignores trend, seasonality, or any sort of business drivers, so this should be treated as a short-term placeholder and not a long-term forecasting solution. The second approach is simple growth-based forecasting. In this method, we start by looking at last year's demand, often month by month, and apply a fixed growth rate to generate the forecast. For example, last year's March demand was 10,000 units. We assume a 5% growth rate, so this year's March forecast becomes 10,500 units. In practice, this technique is most commonly used for low volume or low impact products. Not every SKU in your product portfolio would deserve the same level of analytical effort. For products that contribute very little to total revenue, have very low volumes, or are relatively stable and non-strategic, it often does not make sense to invest time building complex statistical models. A common real-world approach is to apply advanced techniques like regression or time series analysis to top SKUs that drive around 80% of your revenue. And for long tail of smaller SKUs, you apply growth-based forecasting techniques. This approach helps balance forecast accuracy, analyst effort, and overall planning efficiency. In this section, we covered a range of forecasting techniques, each with a different set of purpose and assumptions. Let's quickly recap what we've learned. We started with simple moving averages, which is smooth historical demand and work well when the demand is relatively stable, but do not handle trend or seasonality very well. We then moved to time series forecasting, which builds on the historical demand but also takes into account trend and seasonality. Time series is quite useful when past patterns are expected to continue into future. Next, we introduced linear and multilinear regression, where demand is explained using business drivers like price, promotions, or marketing activity. These techniques are especially useful when future demand is expected to change due to planned business actions. We also covered two simple rule-based approaches: simple extrapolation, which assumes future demand will look like the most recent past, and is mainly useful for discontinued products or newly launched products where we have very limited data history. We also talked about simple growth-based forecasting, where we apply a fixed growth rate to last year's demand, often used for low volume, low impact SKUs where building complex models is not justified. Now, an important point to emphasize is this. There's no single forecasting technique that is best for all the products. Different SKUs behave differently. Some are stable, some are seasonal, some are driven by price or promotions, and some simply do not justify advanced modeling. This brings us to the next part of this course. In the next section, we'll focus on forecast segmentation, that is how to group SKUs based on their characteristics, and how to decide which forecasting technique should be applied to which products. This is where forecasting moves from knowing the tools to using the right tool for the right situation. So far, we have learned multiple forecasting techniques. We have seen moving averages, time series forecasting, regression-based forecasting, and a couple of simple rule-based approaches. Now comes an important question. Should we apply the same forecasting technique to all the SKUs in our product portfolio? The answer is almost always a no. And this is where forecast segmentation comes in. Forecast segmentation is the process of grouping products based on their characteristics and deciding which forecasting technique makes the most sense for each group. The idea is simple. Different products behave differently, so they should not be forecasted using the same technique. Some products are high volume, business critical, and drive most of the revenue. Others might have small volumes, are relatively stable, and might have very limited impact on the overall results of the business. Treating all of them same is inefficient and even counterproductive. There is no single correct way to segment forecast, but in practice, planners often look at few common dimensions. For example, business importance, which means looking at the revenue contribution of the product, their volume, or their strategic relevance of the product. Demand behavior, is the demand stable or volatile? Is it seasonal or non-seasonal? Data availability, whether we have good amount of data available for the product or no. And driver influence, whether the demand is strongly impacted by price, promotions, or other factors. Using these dimensions, SKUs can be grouped into segments that behave similarly. Let's walk through a practical example. Imagine you're responsible for forecasting 200 SKUs. The first step is to decide which SKUs are business critical and which are not. A very common approach here is to use the Pareto 80-20 principle. Roughly 20% of your SKUs might typically drive around 80% of the revenue. The remaining 80% of the SKUs are the long tail SKUs. For the long tail SKUs who have very low contribution to the revenue, it usually does not make sense to invest heavily in complex statistical models. These SKUs are often forecasted using simple growth-based forecasting approach or simple extrapolation, especially if the product is new or is being discontinued. Now let's focus on the top 20 SKUs that drive most of the revenue. For these SKUs, we need to decide which forecasting technique we want to use, and that decision depends upon the demand complexity. You can broadly classify demand as high complexity or low complexity based on a few questions. The first question is about whether the demand of your product is stable or volatile. If your product has a smooth, stable demand that does not have a lot of fluctuations and is quite resistant to impact from external factors, then your product has low demand complexity. Volatile demand, on the other hand, means the product has high complexity. Second question is about data availability. If you have limited historical data or noisy data, then this is a complex product from demand forecasting perspective. If you have a long, clean historical data, then this renders low complexity. Next question is about driver influence. If the demand of your product is sensitive to price, promotion, or other business factors, and these drivers are expected to change in future, then your product has high complexity. Otherwise, if the demand is insensitive to external drivers, or drivers are expected to remain quite similar to how they were in the past, then product has low complexity. Using this logic, high complexity SKUs justify regression-based approaches. Low complexity SKUs can be handled well with time series or smoothing methods. So the key takeaway from this lesson is forecasting is not just about finding the best technique, it's about finding the right technique for the right product. Forecast segmentation helps you allocate forecasting effort where it matters the most and keep things simple where complexity does not add a lot of value. So far, we have talked about forecasting techniques and how to choose the right one. Now let's talk about an equally important question, that is, at what level should the forecast be created? This is exactly what we mean by forecast granularity. Granularity refers to how detailed your forecasts are. In general, best practice is to always plan at the lowest meaningful level of the product and time hierarchy. That usually means forecasting for each and every SKU in your product portfolio and at a monthly level or sometimes even weekly or daily level, depending upon the type of business you're working with. We already touched on this idea briefly in the previous lesson when we talked about macro versus micro forecast. Imagine you're working for a company with 200 SKUs that are divided into 4 categories. It might be tempting to take a shortcut and set up the forecast on a category level and on a quarter level. However, this will not be translatable into operational plans. For production planners to produce the right products at the right time, you need to set up the forecast on an individual SKU level and at a monthly level, or sometimes even by week. In some cases, you may also want to forecast at a customer level. For example, if you have 3 or 4 large strategic customers who behave very differently from the rest of the customer base, it might make sense to plan for those customers separately and group the remaining small customers together into one group. Another important principle is that you can always aggregate a granular forecast, but you cannot reliably disaggregate a forecast that was built on an aggregated level. If you forecast at a high level first and then try to break it down later, you often introduce arbitrary assumptions and bias. By forecasting at the lowest level first, you preserve the true demand signals. You can then later on aggregate SKUs into categories, customers into regions, or months into quarters, depending upon who needs the information. So the key takeaway is forecasting should be done at the level where decisions are actually made. Granular forecasts support operations, improve execution, and reduce downstream surprises. With this foundation in place, let's now talk about how far into the future should we forecast. Now that we understand the level at which the forecast should be built, let's talk about how far ahead should we forecast. This is known as the forecast horizon. In most organizations, demand forecasts are created for the next 12 months. In many companies, this may extend to 15 or 18 months as well, especially to align with the budgeting, capacity planning, or supplier contracts. The right forecast horizon depends heavily on the nature of the products and industry you're working in. For example, in industries with short product life cycles, such as fashion, cosmetics, makeup, very long forecast horizons may not add much value. Because products may change, they might get discontinued or go out of fashion very quickly. So even if you plan for the next 18 months in advance, it might not bring a lot of value. On the other hand, in industries with longer product life cycles, a short forecast horizon can be too risky. In these industries, you might have longer lead times for the raw materials, or you might need to invest in equipment for future. Or let's say your suppliers might be interested in having an earlier visibility. So a longer-term forecast horizon can be helpful in this case. It's also important to understand that not all the months in the forecast horizon are used in the same way. The near-term horizon, typically next 2 to 3 months, are very critical. These plans are often locked for production and have very limited flexibility to change them. For example, imagine you're in the January of 2026. You will prepare a forecast for the next 12 months from Jan 26 to December 2026. The forecast for the immediate next 3 months, that is from Jan 2026 to March 2026, is the near-term forecast. Once you tell your production teams that this is the demand number that you're expecting from January to March 2026, you cannot change it frequently because production teams will formulate their plans and might even have started executing them. The midterm horizon, which is usually from 3rd to 12th month, is used for more strategic decisions, like supplier capacity planning discussion, raw material commitments, equipment utilization, or workforce planning. The further out the forecast goes, the more directional it becomes, but it still provides valuable signals for planning. Setting the right forecast horizon helps balance accuracy, flexibility, and decision-making needs. Too short of a horizon can limit visibility and can lead to reactive planning. A very long horizon, on the other hand, can create a false sense of precision. The goal is not to be perfectly accurate far into the future, but to provide early signals so the business can prepare. So the key takeaway is that forecast horizons should be long enough to support decisions, but not so long that they create unnecessary complexity. In the next lesson, we'll look at forecast governance, where we talk about how often the forecasts are updated and how companies manage forecasting as a rolling process. So far, we have talked about how to build forecast, how to choose the right techniques for different products, and we also explored the concepts of forecast granularity and forecast horizon. Now let's talk about something equally important, that is how forecasts are updated and managed in organizations. This is what we refer to as forecast governance. In practice, forecasts are not created once and forgotten. Most organizations update their forecast on a regular basis, typically once every month. Each of these updates is often referred to as a forecast cycle. For example, the forecast prepared in the month of January might be referred to as January cycle. The forecast prepared in February might be called February cycle, and so on. In each cycle, you plan for the next forecast horizon. For example, assume you're in the month of February 2026 and the forecast horizon for your company is 12 months. Then in the February cycle, you will set up the demand forecast from February 2026 to January 2027. In the March cycle, you will have the forecast demand from March 2026 to February 2027, and this continues every month. This is what we refer to as the rolling forecast. Now, there's an important concept you need to keep in mind, which is calendar landing versus forecast horizon. Here's an important nuance. Management might not always ask, what is the forecast for the next 12 months? Very often, they might ask something like, what is the expected landing for the year 2026 based on the March forecast cycle? Let's think about how to answer this question. In the March cycle, we have the forecast numbers from March of 2026 to February 2027. But the question is specifically about the calendar year 2026. So first, you need to ignore the months that fall outside of calendar year 2026. In this case, it's January 2027 and February 2027. That leaves you with forecast values from March 2026 to December 2026. To complete the full year view of the year 26, you need to add actual numbers from January 2026 and February 26. This brings us to an important governance principle. In every forecast cycle, the most recently completed month is actualized, meaning it is converted from forecast into actuals, and the forecast is extended 1 month further into the future. So in each cycle, 1 month becomes actual and 1 new month is added at the end of the forecast horizon. This ensures that the forecast is always anchored to the latest known reality and is continuously looking forward. This ongoing process of actualizing the latest month and extending the forecast horizon 1 month further is what creates a rolling forecast. Now, forecast governance is not just about updating numbers, it's also about reviewing and understanding the changes. In most organizations, numbers from the current forecast cycle are always compared to the previous forecast cycle and the last year's actual numbers. This helps answer questions like, why did the forecast change versus last month's cycle? Or is the business growing compared to last year? Or the changes driven by demand, pricing, or assumptions? These comparisons are critical for transparency and alignment. A good forecast governance ensures that forecasts are updated consistently, assumptions are visible and documented, changes between the cycles are well understood, and decisions are based on a single aligned view of demand. Without governance, even the best forecasting model can fail. So the key takeaway from this lesson is that forecasting is not just a one-time calculation, it's a rolling governed process that evolves every month. In the next section, we're going to start building an automated forecasting model in Excel. Understanding the forecast governance will help you clearly see why the model is structured the way it is and how it supports the monthly forecast cycles in practice. Before we start building the model in Excel, I would like to walk you through how the final output looks like. The model we are going to build produces a forecast for the next 12 months or whatever forecast horizon you want to work with. There are three main inputs we will need to give to this model: the actual historical demand data for each product of your portfolio, a forecasting technique which we want the model to use to forecast the demand for each product, and a forecast of price and promotion plan for each of the products. Once we give these three inputs to the model, it will produce forecast for the next 12 months depending upon the forecasting technique that we select. Let's see how it works. We have 4 sheets in this file, and on these sheets we need to perform a few simple steps for the model to work. In the first step, we'll head over to the first sheet, which is called historical data, and here we need to update the actual historical demand data by product, month, and year. We need to provide sales volume, price, and whether the product was on promotion or not. The information about price and promotion is quite important because it can be used for linear regression. Let's bring in historical data for at least 12 months. Once we have uploaded the historical data, the second step is to go to the mapping sheet. In the first column where it says product code, we need to write in the product codes of all the SKUs in our portfolio. In the column next to it, we need to define which forecast method we want the model to use to forecast that particular SKU. In this example, I have 15 SKUs in my portfolio, so I will mention the codes for that. And for each SKU, I will designate a specific forecasting technique. In the third step, we need to make sure that for each SKU in our portfolio, we should have a price and promotion forecast. This is important because let's say if we are selecting linear regression as a forecasting technique for any of the SKU, the system will need to know what price and promotion are we planning to sell the product at in future so it can calculate the forecast demand using regression analysis. Here, I have updated the price and promo forecast for all the SKUs. Once that is done, I'm going to head over to the model forecast sheet, and here we can see that in the first 12 months, we have the 12 months of actual historical demand data, and next to it, we can see the forecast for the next 12 months, which is calculated using the forecasting method we defined in step 2. Now assume we are in the month of February 2026, and we have the actual demand data for January 2026. And we're now working to set up the February forecast cycle, which means our forecast horizon now runs from February 2026 to January 2027. Let's see how the model works with that. We'll need to follow the same 3 steps. I will first go to the historical data sheet and update the January 2026 actual demand numbers right at the bottom of the table. In the second step, we need to make sure that all the SKUs of the portfolio are here on the mapping sheet, and for each one of them, a forecasting method is defined. And in the third step, we need to make sure that on price and promo forecast sheet, we have a price and promo plan for the entire forecast horizon. The forecast horizon has now shifted, and it includes one additional month, which is January 2027, which we do not have here on the sheet at the moment. So I'm going to add that. Now, once we have done that, I'll again go over to my model forecast sheet. And here I can see that the model has automatically detected the latest actual month and shifted the forecast horizon. It's giving us the forecast from February 2026 to January 2027. Let's go ahead and start building the model. I'll first set up a new Excel file. For now, I will call it forecast modeling. First of all, we'll set up the sheet where the user is going to input the actuals data. I'll name this sheet as historical data. And here I'm going to provide the structure in which the actuals data should come through. Now let's bring in some historical data as well. I do have the historical data for 12 months of the year 2025. So I'm going to bring it in and paste it here. Now let's go straight away to the sheet where the forecast is going to get generated. I'm going to add a new sheet. I'll call it model forecast. Here in the first column, I will have product codes. For now, let's imagine we are working on January 2026 forecast cycle, which means our forecast horizon will be from January 2026 to December 2026. So I need 12 months over here along the column headers from Jan 26 to December 26, which is our forecast horizon. However, to support our forecast calculations, it's going to be helpful if you can also have last 12 months of actual historical data, which will be from Jan 25 to December 25. For now, I'm going to hard code all the date values. These dates that I've pasted here, they look like numbers, but technically they are dates. Whenever you write dates in Excel, they're internally stored as numerical value. Basically, these numbers indicate the number of days that have passed since January 1st, 1900. If I select all of these data points, go to Home tab, and format them as dates, you will see that this data gets converted into proper looking dates. I don't need these dates in long dates format. I just need first 3 characters of the month name followed by the year number. So I'm going to select all these data points, press Ctrl+1 on my keyboard, go to custom formatting, and here I'm going to put the notation in which I want to see the dates. I will put M followed by 2 Ys. This will give me the date in my desired format. Also, the first 12 months here will be the actuals data. The next 12 months, which is from Jan 26 to December 26, will be the forecast data. So let's color code them to show the difference. Now let's bring in all the SKUs that we are working with. I know that I have only 15 SKUs in my portfolio. For example, if I go to the historical data, apply a filter. To apply a filter, you can go to the Data tab and click on Filter. I use the keyboard shortcut Alt-DFF. Now, if I filter down, I can see that in total, I have 15 SKUs. And each SKU has a SKU code. It starts from SKU001, goes all the way to SKU015. So if I want, I can actually write SKU001, SKU002, and so on. However, these values are hard-coded. Tomorrow, if there is a new SKU, or if the SKU name changes, or if one of the SKUs get discontinued, the list will not get updated because the values are hard-coded. So we want to make it dynamic so that whenever there is a new SKU added in the historical data, anything like that, then the list over here should get updated because our forecast should be generated on the most up-to-date data. So how do we get a list of SKU from the historical data sheet itself? One way to do that is to use the unique function and select all the cells. We know that our data starts from row number 2. The first one is just a heading, so I'm going to ignore it, and I'll go all the way down. And also, I won't just stop where the data is stopping right now, because later on I know we will be adding data over here for the new months as they come across, or as the new months get actualized. So I'm just going to drag it down all the way and maybe go up until row number 2000. Depending upon how much data you have, you can select accordingly. So now we have a list of 15 SKUs that is getting picked up dynamically from the historical data sheet. However, we have one small problem here. At the bottom of this table, you can see that there is a 0 value. This is because some of the cells that we passed into the unique function were empty. So Excel is evaluating all of them to a 0, and we want to get rid of that. To do that, we'll need to use a function in Excel, which is called the filter function. In the next lesson, we're going to learn about that. Let's explore the filter function in Excel. Filter function helps you filter a range of cells or table with a certain criteria. I have a table here with 3 columns: order ID, region, and sales amount. Let's assume that from this table, I only need those rows where the order ID is not equal to ORD018. I can do that using the filter function. The filter function has 2 mandatory arguments. In the first argument, we need to pass in the table or the range of cells which we want to filter. In the second argument, we need to define the criteria based on which we want the table to be filtered. So let's go ahead. In the first argument, I will pass in the range which I want to filter. For now, let's say I want to return only the values from the first column of this table, so I will pass in the entire first column as the first argument. In the second argument, where we need to define the criteria, I will again refer to the first column, put in a not equal to sign, and write the order number which I want to filter out. In this case, ORD018. And there we go. We have all the order numbers here, except for the one we asked the function to filter out, which is ORD018. Now let's say we want to filter the table with multiple criteria. We want to filter out order ID 018 as well as order ID 017. This can also be done using the filter function. If you have multiple criteria with which you want to filter the table, then in the second argument of the filter function, you can write the first filter criteria, wrap it inside parentheses, put a asterisk sign, and then write the second filter criteria, again wrapped inside parentheses. Let's go ahead and do that. I will wrap the first filter criteria inside brackets, put a asterisk sign, then I will write the second filter criteria, which is order ID not equal to ORD017. Again, I will wrap it inside parentheses, press enter, and there we go. We have all the values except for ORD017 and 018. Right now, we are retrieving values only from the first column of the table, but that is not necessary. We can retrieve the entire table or all the columns of the table as well, where order ID is not equal to 018 or 017. To do that, in the first argument of the filter function, we can extend the array to include the full table. Now, if I press enter, we will get the full table where the order ID is not equal to 018 or 017. If I remove the second condition, then I will get all columns of the table with order ID 018 filtered out. Now let's say I want to get all rows from this table that relate to North region. To do that, in the second argument, I will select the second column of the table because that is where the region name sits, and put criteria equal to North. So basically the function is going to take the entire table, and from this table it will return only those rows where the region name is equal to North. Now let's say I want to return those rows of the table where order amount is greater than 1000. So in the second criteria of the filter function, I will give reference to the third column of the table, put greater than sign, and then write 1000. This will return the table filtered with only those rows where the amount is greater than 1000. We can also put multiple conditions on multiple columns as well. For example, let's assume you want to return those rows of the table where region is North and order value is greater than 1000. Since we have two conditions, we will wrap the first condition inside parentheses. Then I'm going to put asterisk sign and put the second condition wrapped again inside parentheses, where we will say region is equal to North. Now we will get the table filtered for North region where order value is greater than 1000. There's a very important point we need to keep in mind when using the filter function. The size of ranges we provide in both the arguments of the function should be of the same length, or in other words, they should have the same number of rows. For example, in argument 1 over here, we have selected cell C7 to E24, which means we're providing row number 7 to 24. Then the ranges that we provide in the second argument should also be of the same length, that is, they should have row 7 to 24. Otherwise, the formula can produce errors. Lastly, let's see what happens when we provide such filter criteria that no rows of the table qualify. For example, I'm going to remove the region condition, and let's say I will put a condition order value is greater than 5000. There are no rows in this table with order amount greater than 5000, so the formula is going to return an error. To handle that error, we can use the third argument of the filter function, which helps us define what we want the function to return when none of the rows meet the filter criteria. So I'm going to put nothing found. When I press enter, the function is going to return nothing found. Now let's solve the problem which we faced in the last lesson. In the first argument of the filter function, I will extend the range to include few empty cells at the bottom. Now from this range, I want to return only those values which are not empty or not equal to 0. So in the second argument, I will pass in the same range and put not equal to blank. We can apply the same logic to the problem we faced in the last lesson, so let's go back there. Coming back to our example, here we have a range, and the problem with this range is that it has 1 0 at the bottom. So what I can do is I can treat this range as the first argument of the filter function, and in the second argument of the filter function, I can exactly say what I did in the last example. That is, I will say return all the values that are non-zero. So I'm going to write in the filter function. The first argument is this range, which has SQ001 to SQ015, and also there is a 0 at the end. Then in the second argument, I'm going to say that return only those rows or those values which are not equal to 0. Close the bracket, and that's it. We have all the SQ list over here. Now the SQ list that we have here stays dynamic. If tomorrow we add a new SQ to the list, for example, let's say on our historical data, we got SQ016, then we don't need to go and manually add it here. The SQ016 will automatically appear. I will do Control Z and go back here. In this course, not only are we going to learn about formulas, functions, and how to use them to build models, we'll also see how to do it in a professional way. I'll teach you the techniques that will help you make your models look clean and professional. In the last lesson, we developed this formula. One of the problems with this formula is that it looks quite clunky and is also difficult to read. If someone who is not familiar with this model reads this formula, they might have a difficult time understanding what's going on over here. Also, later on, let's say if you hand over this file to someone else on your team, it won't be easy for them to decipher this formula. Over and above, getting the list of SQs from the historical datasheet is something we'll be doing quite often while building this model, which means that you might have to rewrite this long and not so easy to read formula quite a few times. So a good approach will be to create a custom function that automatically retrieves the list of all the SQs from the historical datasheet. Let me show you how it looks like. Here in this file, I'm using a function called list all historical SQs. If someone looks at it, it's immediately clear what's going on. And not only it's readable, it's reusable as well. So for example, let's say in some other place in this workbook, I again want to retrieve all the SQ list from the historical datasheet. I don't need to rewrite the full formula. I can just write list all SQs historical data, press enter, and that's it. So this approach makes formulas readable and also improves the reusability. Let's see how we can do that. First of all, I will freeze the cell references in the formula that we created in the last lesson. I can also increase the range of the formula. For now, we kept it to 2000 rows, but just for the safe side, in case in future we have more SQs in our model, I will increase the range to 20,000 rows. Now I'm going to copy this entire formula, and then I will create a new name. I'll go to Formulas, Name Manager. I'll create a new name, and I'll name this List All Historical SQs. And here I will write the formula that we just copied, click on OK, close it. We can see that yes, we have this name defined. Close it over here. Now, if I want to get the list of all the SQs, I just need to write list all historic SQs. And there we go. This is far more readable, plus it's reusable as well. As the next step, we need to get the actual sales volume for the first 12 months. We'll be needing this historical data to perform the moving average and other forecasting calculations. We have the sales volume on the historical data sheet. However, we cannot just copy the values from that sheet and paste them here as hard-coded values. We want to keep the setup dynamic, which means that let's say if tomorrow the month name in the column header changes, or let's say the SQ code in the row header changes, then the volume that is being picked up from the historical data sheet should update automatically. To solve this problem, we can use a function called Xlookup. Let's do a quick overview of how the Xlookup function works. The Xlookup function helps you look up a specific data from a given table. Let's say I have a table here. From this table, I need to get the value for the month of February for SQ001. And I want to get this value here in this cell. This can be done with the help of an Xlookup function in a dynamic way. Let's first understand a few terminologies. The table from which you want to retrieve the values is called the lookup table. In this case, the lookup table is this one. The value based on which you want to retrieve the values from the lookup table is called the lookup value. In this case, the lookup value is SQ001. The column of the lookup table which has the lookup values is called the lookup array. Here in this example, the first column of the table is the lookup array. And the column of the lookup table from which you want to bring or retrieve the value is called the return column or the return array, which is this one. The Xlookup function has three mandatory arguments. The first argument is the lookup value, which in our case will be SQ001. The second argument is the lookup array, which in this case will be the first column of the lookup table. And the third mandatory argument is the return array, which in this case will be the third column of the lookup table. Let's go ahead and update this in the function. Once I press enter, I will get the value for the month of February for SQ001 in this cell. And the setup stays dynamic, which means that if I change the lookup value to SQ002, the retrieve value updates dynamically. If I write SQ001 here, SQ002 over here, and then I drag the formula after freezing the cell references, frozen the references to the return array and the lookup array, but I have kept this one dynamic so that it moves down when I copy the formula. Now, if I copy the formula, see that lookup value has a dynamic reference, so it's going down. Others are fixed, and now we are getting the value for SQ002. So now the SQ value is dynamic. That is, if I change the SQ code, the retrieve value updates automatically. But the month which we have at the top is not dynamic. For example, if I change the month to January, the value doesn't update automatically because the reference to the return array in the Xlookup function is linked to February column of the table, and it doesn't adapt automatically. Now, there are a couple of ways to solve this problem. One of them is to use the index function, which we're going to explore later in the course. Another way to solve this problem is possible if your data in the lookup table is arranged in a vertical format. Let me show you what I mean by that. Let's go to the second sheet in this file. Here, I have exactly the same data which we had on the previous sheet. It's just arranged in a different structure. On the previous sheet, the months were arranged in the column headers and the SQ codes were in the row headers. Now, in this structure, we have two columns. The first column is for the SQ codes. Then we have second column, which has the month names. And then there is a third column for the sales values. In this situation, we can set up a lookup function in a way that both the values, that is the SQ code as well as the month name, will stay dynamic. First, let me show you what happens if we apply the Xlookup in the same way like we did before. That is, I will select SQ code as the lookup value, first column of the lookup table as the lookup array, and the sales column as the return array. Once I press enter, we will get the January value, because basically the function is picking up the first value that it encounters for SQ001. It doesn't yet know that we are looking for the value for the month of February. So to achieve a fully dynamic setup, we can use what is called a combo technique. On the right side over here in an empty cell, I will set up a helper cell where I will create a combination of SQ code and month name that I want to look up. So I will take the SQ code, put an ampersand sign, and put the month name. Now, in the lookup table as well, I'm going to create a new column which will have the combination of SQ code and month. Now the combo value from the helper cell becomes our lookup value for the Xlookup function. The new combo column that we have created in the lookup table becomes the lookup array, and the sales column will be the return array. Let's go ahead and update the function with this. With this setup, the month name also becomes dynamic. For example, if I change the month name, the value updates accordingly. With this formula, we can also create bigger ranges here. For example, I will put SQ001 to SQ003 in the row headers, and I will put January and February month names in the column headers. And instead of setting up a helper cell, what I can also do is just take the formula that I'm giving in the helper cell and put it in over here. I will freeze the column reference of the SQ name because I want this formula to move down. And over here where I'm referring to the month January, I want it to move rightwards, but I don't want it to move down. Now, if I copy and paste this formula, you will see that the formula moves dynamically and you get the right set of values in your result. So lookup function is very helpful in looking up the data from different tables. Coming back to the problem that we were dealing with, here I want to pick up the historical sales data from the historical data sheet. I want to pick up the sales value for a given SQ and month. So if you look at it, we want to pick the value over here in this cell, for example, in this cell, which corresponds to SQ001 and for the month of January 2025. So there are two lookup values, not just one. And if I go to the historical data, I have a column dedicated for SQ name. I also have the data for month and year, based on which I can calculate the date, but I do not have a combo column which combines both the SQ name as well as the month name. So it's not possible for me to do the lookup in this situation. I will need to develop a combo column. So here I'm going to say SQ date combo. I will color code it differently to indicate the user that they don't need to update anything over here. This will be automatically calculated based on the formula. Here, I'm going to create a combo of SQ name, and I need to bring in the date, because the reason I want to bring in the date is because over here as well, we have dates in each of these cells. So since we will be looking up the sales value based on these cells which have dates, we need to have date over here as well. So I will take the SQ name, then combine it with date. Basically, the date function helps create a date value. It has 3 arguments: year, month, and day. For the year, I will pass in the value from the year column. For the month, I will pass in the value from the month column. And for day, I will put 1 for now. So reference to A2 brings in the SQ code. Then we have the ampersand sign. And after that, we have the date function, which creates a date value for us based on the year, month, and day we have passed in. Once we enter this, we get this particular value. The SQ001 is fine. It's coming from cell A2. But after that, we have this numerical value. This doesn't seem like a date which we have on the model forecast sheet, but that is okay because as I mentioned before, dates in Excel are internally evaluated as numeric values. This number indicates the number of days that have passed since 1st January 1900. In fact, if you go to the model forecast sheet, and over here, let's say I convert this particular date into a number, we will see the same number that we see on the historical data sheet where we created that combo formula. So the lookup will still work because internally, both these dates are evaluated as the same numerical value. Now I need to drag this formula down. I'll bring it down all the way, and later on my data might expand in future as well. So not just up until row number 181, I'll go further down and expand it to a lot more cells so that in case if the data comes in future, it automatically updates and the formula works. However, as you saw that the cells where there's no data right now and they are blank, it's throwing up an error. So to clean up our file, I'm going to use an if error function. In the if error, the first argument is what we want the formula to evaluate, and second argument is what we want the formula to return in case if it runs into an error. Now I'm going to drag the formula all the way down, and there we go. For the cells which are empty, there's nothing, and for the cells where there is a data, we will be getting the data accordingly. So now we have this column, and based on this column, we can perform the lookup that we want. So here I'm going to come and put Xlookup formula. In the lookup value, I will pass in the SQ name. I will freeze the columns here, and I will pass in the month or the date. Again, I will freeze the rows over here. This is my lookup value. The lookup array is my column which has the combo code, and the return array is the sales. Again, I will freeze this, close the cell, and there we go. Now I can copy this formula to all the cells. Or I've dragged the formula down up until only row number 17 because right now we have only 15 SQs, but as I mentioned, later on this file can expand as well. So just to be on the safe side so that the formula works in those situations as well where the file expands, I'll drag it down. But as you will see, once I drag it down, it runs into error because Excel is not able to find this lookup value. So again, I'll wrap up this formula inside an if error function. And in the second argument, I will say that in case if the formula runs into an error, it returns nothing. Now I'll copy this formula to the entire range. And there we go. Later on, if any new SQ comes over here, these cells will automatically produce the results. But as long as new SQs are not there, it will not run into an error. It will keep your spreadsheets clean. We developed this lookup formula in the last video. Again, we can say that this formula is a bit unreadable and not very user-friendly. Wouldn't it be great to have a formula like this which says get historic sales, and in this formula I'm passing in two arguments, that is the SQ name and the month name, and that's pretty much it. The function is retrieving the sales volume for us from the historical data sheet. I think we can all agree that this is much cleaner and better looking approach. Now there is no function in Excel by default which is called get historic sales. This is a custom function which we'll need to develop. To create custom functions, we can use something called LAMBDA. To create a LAMBDA, first of all, we need to make up our mind that what are the arguments that we want to pass into the function, the custom function that we're planning to develop. In this example, the inputs that we would want to give to the function are the SQ code and the month name. Once you know the inputs, you need to know the expression that you want your new custom function to perform. Here we know that as well. We want Excel to do an Xlookup using those SQ and month name that have been inputted by the user and pick up the value from the historical sales data sheet. In other words, this is the expression that I want the new function to perform. To create a new function, I will first write the lambda, and then I will input the two arguments that I want the function to take in. First argument is going to be the SQ, second one will be the month name. After that, I need to provide the syntax or expression that I want my custom function to perform. So I will paste in the expression which we just created in the last lesson. Also, in the expression that I have put in, I don't want the expression to take in the values from cell A3 and cell B2. Instead, I will want the function to take in the SQ and month name that the user has passed into this new custom function. So again, let's have one look. We are saying that we want to create a new function which will take in two arguments, SQ and month. And once we give this function two arguments, SQ and month, it should perform this particular expression. And in this expression, it will slot in SQ and month, which are passed into this function over here in this particular spot. Basically, it will concatenate the SQ and month name, and then it will go to the historical data in column H and column D and try to look up the actual sales value there. Let's close the formula. And once I press enter, it will not work right now because we need to do one more step, that is to create a name of this function. So I'm going to copy everything over here. Then I'll go to Formulas, Name Manager. Here we already created one name. Now I'm going to create the second name. I'll call it Get Historic Sales by SQ and month. And in this function, I will paste exactly what we just created. If you want, you can this is exactly the formula that we just wrote above. So I'm going to click OK. So now we have this new function created. I'm going to close it. I will delete it. This was just for the reference of explaining the formula. Now, instead of writing the Xlookup function, I can actually delete all of this. And I can use my newly created function, which is Get Historic Sales by SQ and month. I need to, first argument is SQ. I need to pass in the SQ. I'll freeze the column reference. Then I need to pass in the month. Here I will freeze the row reference. And that's pretty much it. Now I can drag the formula down. And voila, it works. I will also drag the formula down a few hundred rows so that in case if in future my model expands, the formula keeps on working. We now have 12 months of actual data for all SKUs. The next step is to build a forecast for each of these SKUs. For this exercise, we'll assume that the forecast segmentation has already been completed, meaning we already have decided which forecasting method to be used for each SKU. The objective of this section is to focus on building strong Excel modeling skills, so we're not going to worry about the forecast segmentation and assume that we already have that in place. To begin, I'll add a new column at the start of the table where we can specify the forecasting technique for every SKU. I'll use the keyboard shortcut Alt-IC to insert a new column. Let's say for the first SKU, we want to do simple extrapolation. For this one, we want to do moving average of last 3 months. Then for this one, we want to do moving average of last 12 months. And for the rest of the portfolio, we want to apply simple growth at the rate of 4%. So to generate the forecast, as you know, it's very simple. For extrapolation, we will just drag the last month's value. For moving average of 3 months, I will take the average of the last 3 months. and drag it forward for moving average 12 months. Again, very simple. Average of the last 12 months, drag it forward. And then for simple growth, let's say if you want to grow everything by 4%, I'm going to take the last year's same month number, multiply it by 1 plus 4%. And there we go. We have the forecast ready based on the forecasting techniques that we have defined in column A. So very good. We have created the forecast for the next 12 months using the forecasting method that is in this particular column. However, the setup is not dynamic because the demand planner who is using this model might actually want to change the forecasting method for different products later on. And the model is not going to adjust automatically. For example, here right now I have assigned simple extrapolation to SQ001, and you can see that the formula is simply extrapolating the latest month's volume, which is great. But tomorrow, if I change this to simple growth methodology, the model is still taking the simple extrapolation. So we want to design the model in a way that if demand planner changes the forecasting technique in column A here, the formula that is used to calculate the forecast in column O to column Z should update automatically. And to achieve this kind of setup, we'll need to have a bit of a grip on Excel's logical functions. So let's do a quick sidetrack to explore the logical functions in Excel. The three logical functions which we're going to explore in this course are if-else, and switch. Imagine I have this data set here. I have salesperson name, region, and monthly sales amount. In the fourth column, I want to tag the performance of each salesperson. The criteria here is that if monthly sales are greater than 60,000, then I want to return high performance. Otherwise, we want to return low performance. This can be achieved via the if function. The if function has three arguments. First argument is the condition we want the function to evaluate. Second argument is what we want the function to return if the condition is true. And the third argument is what we want the function to return if the condition is false. I want the function to test whether the sales is greater than 60,000. So that becomes my first argument. If the sales is greater than 60,000, then I want the function to return high. So in the second argument, I'm going to key in that. And if the sales is not greater than 60,000, that is, the condition is not met, I want the function to return low. So I'll put that as the third argument. Now let's press enter and drag the formula down. And that's it. We have the performance tagged as high or low depending upon the sales value. Now let's add another column for commission. In this column, we want to bring in the commission percentage, which depends upon the region. If the region is north, we want to give a commission of 5%, south should be 6%, east should be 4%, and for west it should be 0. This means that we want the function to first check if the region is north, and if it is, it should return 5%. If it is not north, then we want it to check whether it is south. And if that is true, it should return 6%, and so on. That means we want the function to evaluate not just one condition, but multiple conditions in sequence. Or in other words, evaluate a certain condition multiple times. There are two ways to achieve this kind of multiple condition evaluation. First option is to use the if-else statement. In the if-else statement, you can put the first logical test that you want the function to evaluate, then you can put the answer you want the function to return if that test is true. After that, you can put the second argument which you want to be evaluated, then the result that you want to be returned in case that argument is true, and then so on. Here we can give the first logical test. So the first logical test is I want the formula to check whether the region is north. And if the region is north, I want it to return 5%. If region is not north, then I want the formula to check if the region is south. If it is south, I want the formula to return 6%. If it is not north and if it is not south, then I want the formula to check whether the region is east. And if that's the case, I want to return 4%. Now I will drag the formula down. You will notice an error in rows where the region is west. No problem, we can wrap the if-else statement inside an error handling function. There are two error handling functions in Excel, if-error and if-NA. They both should work fine over here, and they both work in the same way. They both have two arguments. First argument will be the expression that we want the function to evaluate. Second argument is the value we want the function to return in case if the expression in the first argument ends up in an error. In this example, I will use the if-NA function. For the first argument, I'll put in the if-else statement which we just developed. In the second argument, I will put 0, which means that if there is an error as a result of the expression in the first argument, I want the function to return 0. There's another better way to handle this kind of situation where we have multiple condition testing, and that is by using the switch statement. Switch statement has three arguments. The first argument is the expression we want the function to evaluate. Second is the value against which we want the function to evaluate the expression. And the third is the result we want the function to return if the expression matches the value. Let's walk through it. For the first argument, which is expression, we want the function to check which region is the formula working with. So I will give reference to the region column. Now I want the function to test whether the region is north. So the second argument becomes north wrapped inside quotation marks. Third argument is the result. This means that if the region matches north, what do we want the function to return? I want to return 5%, so I'll key in that. These are the three mandatory arguments of the switch statement, but we can put more as well in this function. The fourth argument, which says value 2, can be used as follows. So if the region is not north, then what do we want the function to do? We want it to test whether the region is south. So in the fourth argument, I will put south wrapped inside quotation marks. And if that is true, that is region is south, we want to return 6%, so I will key in that as the next argument. If the region is not north and neither south, then what do we want the function to do? We want it to test whether the region is east. So let's put that in. And if it is east, we want to return 4%, so I'll key that in. Last argument of the function is the default value, which basically means what do we want the function to return if it is not able to find north, south, or east. We want it to return 0 because the last possibility is that the region will be west, for which we want to return 0%. Now I'll close the formula, press enter, and drag it down, and we have the commission tagging in place as well. Now we will take the learnings from this lesson and apply it to the problem we saw earlier. We will use the switch function to handle different types of forecasting techniques. Basically, we want Excel to adapt the forecasting calculation depending upon what forecasting technique is described or mentioned in the column A of the sheet. So let's see how we're going to build that. So I will put in the switch function and I will say, have a look at this. If this is simple extrapolation, then just simply bring in the value from the last month, because that is what simple extrapolation is. If it is not simple extrapolation, then check whether it is MA3. And if it is indeed MA3, just take the average of the last 3 months. If it is not also MA3, then it might be MA12. Check if it is MA12. And if it is MA12, then bring in the average of all the values from the last 12 months. And if it is not also MA12, then for now I've just included 4 forecasting techniques, so I know that it's gotta be simple growth. And if it is indeed simple growth, then I just want the function to take in the last year, same month number, multiply it by 1 plus 4% growth. I'm not putting any default because I know that there are only 4 forecasting techniques that we are working with right now. So the forecasting technique has got to be one of them that I've mentioned. Now I'm going to copy and paste this formula to all the cells. There's something went wrong. Before I do that, I'm just going to freeze the reference to column A. Now I can copy and paste this formula everywhere. Also, I'm just gonna format the numbers a little better and bring them to 1 decimal point. So here we have made the setup dynamic. So let's say right now, as we can clearly see for SQ001, it is doing a simple extrapolation, but now the setup is dynamic. If I make it simple growth, the numbers will change and it will calculate growth based on last year. If I make it emit 3, it will take the moving average 3. If I again make it simple extrapolation, it will take simple extrapolation technique. Similar to how we did for the first 12 months of actual data, where we drag the formula to a few extra rows so that the model works even if the data expands, I'm going to do the same for the forecast formula as well. But you'll notice that if I drag the forecast formula right now, it gives an error for those rows where there is nothing defined in column A. To fix this, we can wrap our switch function inside an error handling function. I will use the ifError function, and the switch function becomes the first argument of the ifError function. If the output of the switch function is a proper value, it will return that. If the output of a switch function is an error, then I want to return blank. So in the second argument of the ifError function, I'm going to key in blank. Now we can copy and paste the formula. So now we have the model, it's dynamic. Once the demand planner changes the forecast method over here, the forecast automatically updates. Also, this portion is also dynamic, which means that if you have more SKUs than 15 that are mentioned here, the model is automatically going to expand. But there is one problem in keeping the forecast methods hard-coded like we have over here. If the sequence of the SKUs changes tomorrow, then the forecasting method might get invalid. Have a look at SQ001. Right now, SQ001 is getting forecasted using simple extrapolation, and that is our intent. But since this is being calculated dynamically, tomorrow the sequence of the SKUs here can change. And that might happen because maybe in the historical data, the sequence of the SKUs is different. Let me show you an example. If I go to the historical data and I pick up all the numbers for SQ001 from here, and I'll paste them at the bottom. And from the top, I will remove all the rows related to SQ001. So basically, the sequence of data has now shifted. Previously, SQ001 was at the top of the table. Now it is at the bottom of it. Now, if you will go to the model forecast sheet, you will see that SQ001 appears at the bottom. And our intent was to apply simple extrapolation to SQ001. But now, since the sequence has changed, it is getting applied simple growth. If you have made the SQ range dynamic, don't keep the forecast method hard-coded here. Keep either both of them hard-coded or both of them dynamic. We definitely want to keep this dynamic because otherwise the SQ list will not get updated as we update the latest historic data. So we want to make this column dynamic as well. First of all, I'm going to undo what I did just now on the historical data sheet. So I've removed the SQ001 from the bottom. Now it's again here at the top and our model works perfectly fine. To solve this problem, we should create a mapping table on a separate sheet, where we will keep both SQ code and forecasting technique hard-coded. Then from that mapping table, we will look up the forecasting technique and bring it here dynamically. If a demand planner wants to change the forecasting technique for any SQ, they will do it in the mapping sheet directly itself. Let me show you how the setup works. So let's go ahead and set up a new sheet over here. I'm going to call it mapping. And here I will have the first column, which we will call product code. And the second column will be the forecast method that we want to be applied to that particular product code. And as I mentioned, to avoid the problem that we just discussed about, over here we will keep both the product code as well as the forecast method hard-coded. These will not be dynamic. So for now, we have only 15 SQs. I'm just going to pick it up from there and paste it over here. Perfect. And then I can also input the forecast methods that we have in the database. So both of these are hard-coded. If the sequence changes in the historical data or anything, this mapping will stay consistent and it will not go off. So how do the demand planners change the demand forecast method? They will basically change it over here, and here it should automatically reflect. Right now this is hard-coded, but we're gonna pick it up from the mapping table. So I'm just gonna remove all the forecasting methods here, and basically I'm gonna put in an Xlookup. I'll say lookup value is this, and this is the lookup array, and this is the return array. And there we go. If I drag it all the way down, it will pick up the forecasting methods for all the SQs. I know that later on in the model, we will need to reuse this formula, which looks up the forecasting method from the mapping table depending upon the SQ code that has been selected. So I will create a custom function right now using LAMBDA, like we did before when we created a custom function to pick up the historical sales data. I will first copy the syntax of this lookup formula. Also note that there is only one input into this formula, which is the SQ code. This will be needed when we are setting up the LAMBDA. So basically, I want to create a custom function in which I pass in the SQ code, and then that function should pick up the forecasting technique from the mapping sheet. I will write the LAMBDA. In the first argument of LAMBDA, I will put in the variable SQ because that will be the input that we'll be giving to the custom function. And in the second argument, I will write the syntax of the lookup function, which I just copied. In the lookup function, instead of referring to cell B3, I will refer to the SQ variable. And there we go. Right now it will not work, which is fine. Now I'm going to copy this entire formula. I'll go to formulas, name manager, create a new name. I'll say get forecast method. And here I'm going to give in the formula that we just created. Click on OK. Now we have the get forecast method created. I'll delete it over here. I'll also delete this. And all I need to do is use the function called getForecastMethod. I just need to give it an SQ name. And once I do that, it automatically picks it up. Now, similar to how we did with column C to column Z, we extended the formulas down, right? Because we knew that later on the model can expand and we might have new products that will come across. So likewise, I can do the same over here as well. I can expand the formula down so that if the new SQs come in, their forecast method automatically gets picked up. But this is not necessary in this particular case. Over here, these were some complicated formulas, but here we have a technique that we can use. That is, instead of giving it only one cell, I will give it the entire range. This is a dynamic range, so I'll put in #, and once I do that, it will automatically calculate. Later on tomorrow, if this range expands, this formula will expand as well. And let me give you a quick example of it. Let's say tomorrow in the historical data, we have SQ xx016. It comes up and it shows up over here, and the formula also gets auto-expanded. The reason why it's showing NA is because on the mapping table we do not have this SQ. If I put SQ016 and let's say I select MA12 as the forecasting method, then on the model sheet it will show immediately. So basically the range of this formula is not dynamic depending upon the range of, or the size of the range of this column. We don't need to drag the formula down further like we have done in column C to column Z. Now I will just undo some of the changes that I did. And come back to the original position. Now let's test it out. If demand planner wants to change simple extrapolation to simple growth, they won't change it over here. They're going to go to the mapping table, and here they're going to change to simple growth. And once they do that, the change will propagate and flow through. And here, as you can see, now the formula is calculating based on simple growth and not simple extrapolation. If I make it simple extrapolation again, it will get reflected over here as well. And also let's see if it's solving the original problem of sequencing as we saw before. What if the sequence of the SQs change? Will this be intact? Yes, it should be. So I'm again going to go to the historical data sheet. Let's assume that SQ1 somehow flows all the way down and it gets deleted from the top. Just because, let's say from the ERP, we get the data this way. If I come to the model forecast, you will see SQ001 has gone down, but the forecast method is intact. It's still applying the extrapolation, which was our intent. So now the sheet is dynamic and it should be free from any errors that can come across due to change in the sequencing. Again, I'm just going to do Control Z of what we did here. We just said that if demand planner wants to change the forecasting technique for any of the SQ, they need to update it here on the mapping sheet. So let's say for SQ009, we want to go with simple extrapolation. While typing in manually like this, there's always a chance of mistyping or misspelling the forecasting technique name. And if that happens, like you can see here, I have misspelled extrapolation, there's a double A instead of a single A, then our model is not going to work and the forecast for this SQ will not be produced. So we want to avoid the possibility of these types of errors. We don't want demand planners to manually type in the forecasting technique name. A better option will be to let them select a forecasting technique from drop-down menu like we can see here. So let's go ahead and build that. To set up a drop-down list, we first need to have clarity about how many and which forecasting techniques we're going to work with. We're going to work with these 5 methods for now. Simple extrapolation, moving average 3, moving average 12, MLR, which is multilinear regression, and simple growth. Now I will select this entire range of cells where I would want the demand planners to be able to pick up the forecasting technique from a drop-down option. I will select a few extra cells beyond the currently populated data so that if model expands in future, it still works. Now with this range selected, I'll go to the data tab and select data validation. Here I will select a list and then the source of list will come from over here. Click on OK. Now you can see that if someone enters simple extrapolation, first of all, they will see that there is this option, but in case if they try to enter the wrong spelling, Excel will not allow it. But beyond everything, they always have the option to select from the drop-down and select the right methodology. So this will avoid errors, input errors from the demand planning side. Now let's select the MLR technique. Let's say for SQ003, I want to go with MLR, and we can make maybe SQ014, we can make it MA12. Okay. Now, if I go to the model forecast sheet, you will see that SQ003 will not have any forecast. And that is because in the switch function that we have input there, we have only defined 4 forecasting techniques. We haven't defined the MLR yet. So in the upcoming lessons, we'll continue building the model and include linear regression forecasting in it. From a previous lesson, you might recall we did multilinear regression with 2 X variables, price and promotion. You will also recall that in MLR equation, we had 5 data points in total. First was the baseline, then we had 2 coefficients, one for each X variable, and then we had forecast values for price and promotion. In this model as well, we will build MLR based on 2 variables, that is price and promotion. This means that we will need the forecasted values for price and the promotion. We want to bring in the price and promo forecast on the right side of this sheet so it can be easily used in the switch formula that we have already set up for the forecast calculation. Let's build the setup step by step. First, I will set up a new sheet and call it price promo forecast. First, I'm going to set up a column for product codes, and I will keep the product codes hard-coded due to the same reason that we discussed before. That is, on mapping sheets like these, where we would want the users to input data, we should always keep the values hard-coded. Along the column headers, I want to put the periods of the forecast horizon. In the current file, our forecast horizon is from January 2026 to December 2026. So I need to bring those periods in. I will take the first month, which is January 2026, and I'll paste it over here. After January 2026, I want to add the next 12 months, and I can do that using a formula called eDate. The eDate function moves a given date by a month interval, which we will define. The function has 2 arguments. The first argument is a date that we need to provide, and second argument is the interval in months by which we want to move the date. So I will write eDate function. In the first argument, I will give reference to Jan 2026, and in the second argument, I will put 1 because I want to have February 2026 here, which is 1 month after January 2026. Let's format this entire range as date. And now I can drag the formula rightwards. From column B to column M, we would want the users to input the price forecast for each SQ, and from column O to column Z, we would want the users to input the promotion forecast. Now let's go ahead and put some forecast values for both price and promotion here. And I'm also going to format these cells in a different color to indicate to the user that these are input cells. Now that we have created this input sheet, we need to bring in the values from this sheet to the forecast modeling sheet so they can ultimately be used in the forecast calculations. First of all, let me freeze the panes. I can do that by pressing the shortcut Alt-WFF, or you can also go to the View tab and select the option to freeze panes. This will ensure that if I scroll towards the right side of the sheet, the leftmost columns stay visible. From column AB, I will set up the columns to bring in the promo forecast. And then from column AO onwards, I want to bring in the pricing forecast. It's helpful to keep these forecast values here because ultimately we're going to be using them in the forecast calculations. Now that the sections are set, we need to bring in the data for price and promo forecast sheet to here. One option could be to use the Xlookup function. An Xlookup function is great when you have only one lookup value. For example, if we wanted to pick up the price and promotion from the price and promo forecast sheet, depending upon the SQ code, then Xlookup would have been very helpful. But in this situation, it's not only the SQ code that we want to treat as the lookup value, we also want to treat the month headers as the lookup value as well. So broadly, what I want the formula to do is that first it looks for SQ001 in the row headers on the price and promo forecast sheet. Then it looks for January 2025 along the column headers. And then at the intersection of this row and column, whatever value is existing there, it picks up that value and brings it on the model forecast sheet. So there are two lookup values in this situation. And therefore, a more appropriate function to use will be the index function, which we already studied about earlier in the course. Let's go step by step. Let's say I want to bring in the value for price forecast for SQ001 for the month of January 2026. I will write the index function, and in the first argument of the index function, I will define the range from where I want the price to be picked up, which is this section on the price and promo forecast sheet. I will just select a few extra cells just in case if the model expands in future, the range that we're defining in the index function is big enough to capture everything. I'll also freeze this array for now. Now, as you know, in the second argument of the index function, we need to put in the row number, and in the third argument, we want to put in the column number from which we want the function to pick up the value. Here, I want to get the data for SQ001 for the month of January 2026. Let's go and check which row and column number of the selected range is this data point located in. SQ001 is in row number 1, and January 2026 is in column 1 of the selected range. So I'm going to put that in the index function. And there we go, we have the price. For now, we have put row number 1 and column number 1 as hard-coded values, which means if I drag this formula down, it will get the same value for all the cells, for all the SQs, which is not correct. We want to set it up in a way that it's dynamic, such that when I drag the formula down, it should pick up the price values for SQ002, SQ003, and so on. This means that I want to make the row number and the column number which we are passing into the index function dynamic, such that it changes depending upon the SQ that is there in the row header and the month or period that is there in the column header of the formula. I would like to have a function that does this job for me. That is a function that looks at the SQ code here in the row headers on this sheet, checks which row in the selected range on the price and promo forecast sheet is that SQ present, and returns that row number. Likewise, the function should also look at the period in the column header over here on this sheet, then check which column in the selected range on the price and promo forecast sheet is that period present in, and then returns that column number. This can be achieved via the xmatch function. Let me show you how it works. Xmatch function has two mandatory arguments. The first argument is the lookup value, and second argument is the lookup array. For the lookup value, I will refer to the column that contains the SQ codes, which is the row headers here on the sheet. For the lookup array, I will refer to the column range where we have the list of SQ codes. So that will be cell A4 to A38 on the price and promo forecast sheet. Once I enter this, it will give me 1, which is correct. SQ001 is situated in the first row of the selected range. If I drag the formula down, it will update the row numbers accordingly depending upon the SQ in the row headers. So for example, SQ002 is in row number 2, SQ003 is in row number 3, and so on. So now I can slot this xmatch function which we have developed here into the row argument of the index function. Now if I drag this formula down, you will see that the price will update accordingly in line with the SQ that we have in the row headers. Now we want to do the same thing for column references as well. Right now we have given first column in the index function, which means if I drag this formula rightwards, all the months will have the price of January because column 1 refers to January 2026. So we want to make the column reference argument of this index function dynamic such that it changes depending upon what period is there in the column headers. But we don't want to make it dynamic just based on the month name. We want to make sure that formula also looks at what metric are we picking up. If you come to the price and promo forecast sheet, you can see that we have 2 columns related to January 2026. This one as well as this one. The first one is related to price forecast. So it's showing price forecast for January 2026. The second one is showing promo forecast for the month January 2026. So we want to make sure that our xmatch function not only returns us the column location of January 2026 alone, but it also looks at the metric that we are talking about while picking up the column reference. To solve this problem, we'll do something similar to the combo lookup, which we learned about earlier. I will set up a combo of price forecast and the period name here on the price and promo forecast sheet in row number 1. This will also become the lookup array of my xmatch function later on. Now let's go back to the index function, and in the column reference argument, instead of hard coding 1, I will put xmatch. The lookup value, which is the first argument of the xmatch function, will be the combination of price forecast, which is the metric, and the period name. The lookup array will be the combo array which we just created in the first row of the price and promo forecast sheet. I will need to make sure that the size of the lookup array in terms of the width is the same that I give in the first argument of the index function. In the first argument of the index function, we selected column B to column AF, so the array for the xmatch function will be the same. I'm just going to select cell B1 to AF1. To make sure xmatch is working properly, we can highlight only that portion of the formula that contains xmatch. So as you can see, in January 2026 column, xmatch is returning 1. Now if I go to the next column, it is returning 2. This means that the formula is working. I will now copy and paste this formula. I want to make sure we have this set up for the promo section as well. So first of all, I'll go back to my price and promo forecast sheet and create a combo array just above the promo columns. Now I can simply copy and paste this formula in the promo section. Now let's talk about the formula extension. Right now we have this formula populated only up until SQ015, but tomorrow, as you know, we can have more SQs, so we want to make sure that the formula extends down if more SQs are added in future. We can achieve that by applying the same technique that we did for column A, where we picked up the forecasting method depending upon the SQ code in column B. The only input going into this index function is the SQ code. The SQ code is a dynamic array. This means that in the index function where I'm passing the SQ code, if I put a hash sign in front of the cell reference, it will extend the range of this index formula automatically depending upon the number of SQs that we have in column B. Let me first delete all the data here. Now here, in front of the cell reference B3, I'm going to put a hash sign, which will help pick up the entire dynamic range. And now I can drag the formula rightwards. Since it's a dynamic range formula, it will extend automatically depending upon the number of SQs we have in column B. So we now have the data for price forecast as well as the promo forecast, which we're going to be using in the MLR equation. Now we need to get three other data points, which is baseline and coefficients for price and promotion. As you already know by now, we can get these data points from the Linus function in Excel. In the Linus function, we have two mandatory arguments, historical data of y variables and historical data of x variables. Once we put that in, the function is going to give us the baseline and coefficients. In this scenario, the y variable is the sales volume because that is what we're trying to predict, and x variables, or the independent variables, are the price and promotion. So how do we slot those in? First, let's work with only SQ001 and get the historical data for sales, price, and promotion. We can get the sales from historical datasheet. We can use the filter function. In the first argument of filter function, I will give reference to the column on the historical datasheet which has the sales data. In the second argument, where we need to define the criteria, I will put reference to the first column which contains the product code, and I will put equal to SQ001. And that's all. We have the last 12 months of historical data for sales volume. And in future, if more months are added to historical data, this will expand as well. Now I can use the same formula to pick up the historical data for price and promo. I will copy the same formula in the price and promo columns, and then just amend the first argument of the filter function. To pick up the price, I will refer the first argument to column E, which contains price, and for promo, I will refer it to column F. Now we can run the regression based on this data. In the Linus function for the first argument, I'll reference the sales data. I'll select cell BD3 and add a hash symbol, which will automatically pick up all the values in this dynamic array. For the second argument where we specify the x variables, I'll use the hstack function to combine the price and promo ranges. In a previous lesson on linear regression, you might recall we used the vstack function to combine the ranges vertically. Hstack does the same job, but it combines the ranges horizontally. And there we go. We now have the outputs, the baseline, the price coefficient, as well as the promo coefficient. Next, I'm going to create custom functions for the formulas we're using here to retrieve historical sales, price, and promo data. Since we're going to be reusing these multiple times, it makes sense to define them once and keep our model clean. To do this, I'll use LAMBDA. First, I'll copy the entire formula for which I want to create a custom function. Then I'll write a LAMBDA function, and in the first argument, I'll define SQ as an input parameter. And in the second argument, I'll paste the formula which I just copied. Inside the formula, I'll replace SQ001 with this input variable that we define, and that is SQ. Now I'm going to repeat the same process for price and promo. Now I'll assign names to these functions. I'll copy the first one, go to Formulas, Name Manager, and a new name. And I'll give it a name like Get Sales Historic for all months. And then paste the formula. I'll repeat the same steps to create functions for historical price and promo. Now I can remove the old formulas and replace them with new custom functions that we just created. So we now have the baseline and coefficients calculated for SQ001. Now we want to do the same for all the other SQs. So how do we do that? The problem with this setup is that here we have the sales price and historic promo values for SQ001. And we are passing in these values into the Linus function, which is giving us the baseline and coefficients. However, we cannot have the values for all the SQs here because we don't have enough space. So a good option would be that in the Linus function, instead of passing these values from here, I can directly pass in the formula that is used to retrieve these values. So instead of referring to dynamic range in BD3, I will take the formula which we have in cell BD3 and slot that in here. The formula that we have in cell BD3 is get historic sales for all months, so I will put that in here. Likewise, I will do the same for the second argument of the Linus function where we are passing in the price and promo values. Instead of these values, I will slot in the functions we just created to retrieve price and promo historic data. Now, even if I delete these values in column BD to column BF, the Linus function continues to work fine. Now I can drag the Linus function down and it will give us the baseline and coefficients for all the SQs. Using these values for baselines and coefficients, we can calculate the forecast using multilinear regression. To do that, I will go into the switch statement, which we had set up before. I will add an extra condition in the switch statement, which is going to check if the selected forecasting method is MLR or not. And if it is MLR, what do I want the function to do? I want it to take the baseline, which is over here, then add to it the coefficient of promotion multiplied by the forecast value of promotion, and then add to it the coefficient of price multiplied by forecast value of price. Press enter, and now I can drag this formula to all cells, but before doing that, I will fix some of the cell references. So when I copy and paste the formula to different ranges, it works fine. Now let's talk about formula extensions. As you might recall, we copied these earlier formulas down to a few extra rows so that in future, if the model expands or new SQs are added, the model and the formulas in it continue working fine. So we can drag the Linus formula down as well. However, there's one important watch out which I want you to keep in mind. Linus is quite a heavy formula, and if you drag it down to, let's say, 1,000 rows or so, it can make your spreadsheet slow and clunky. So one great workaround is that we only let the Linus function work where the selected forecasting technique is multilinear regression, because that is the only place where we use the output of the Linus function. That way, the number of times the Linus formula works will reduce significantly. This can be achieved via the if statement. In the first argument of the if function, where we need to put in a logical test, I will put A3 not equal to MLR. Which means I want the formula to check if the forecasting technique in cell A3 is not MLR. And if it is not MLR, I want it to return 1, or I can return anything else as well, for example, blank. And if this condition is not true, which means that the forecasting technique is MLR, then we would want it to return the output of the Linus function. Let's enter. And copy it down. Now, as you can see, Linus only works where the selected forecasting technique is MLR. Now, I'm going to drag the formula down just like I did for the other ones. I dragged this down up until row number 107. So I'm going to do the same for here as well. So as you can see, it's just showing 1 right now. If you don't want to show 1, you can also show just blank, like this, and that should do the job as well. So let's say I want to change SQ002 as well to MLR. Right now it's showing a volume of 822, volume forecast of 822. If you want to switch it to MLR, I'll go to the mapping sheet, and on the mapping sheet I'll select MLR. I'll come back, and now the forecast will be 787 because the forecast methodology has changed. Likewise, let's try it out with SQ001 as well. For SQ001, I want to do the same thing. I want to go with MLR. If I come back, it's 544. Whereas if I go back to simple extrapolation, the number was different. There's one more thing which we have to make dynamic, and that is the simple growth. Right now we have hard-coded 4%, but demand planners might want to put in any other growth percentage. So we can do that. That's not very difficult. I'll go to the mapping tab, and here, just next to the simple growth, I will create an input cell where I will expect the demand planners to put in the growth rate that they want to be applied to all the SKUs that have simple growth as the forecasting method. So I'll put in 4% here for now, and I'll name this cell as growth cell by going into this particular box. Now this cell is called growth cell, and everywhere in the workbook where I write growth, it will return me 4%. So I'll go to the forecasting sheet, and here, instead of writing 4%, I will write growth and press enter. Now I'm gonna paste this formula everywhere, and also I will drag it all the way down. Perfect. Right now, we have developed this model assuming that we're working on January forecast cycle, which means that our forecast horizon is from January 2026 to December 2026. But tomorrow, once January actual data arrives and the user is now working on February forecast cycle, and they paste the January actual data here at the bottom of the historical data sheet, we would want the model to expand and adjust such that the first 12 months of actual should be from February 2025 to January 2026, and the forecast horizon should be from February 2026 to January 2027. So how do I do that? I want this particular cell to be picked up dynamically. This column over here should always be the latest actualized month. How do I do that? I can go here and I can see what is the latest month. Right now there is no date over here. So on the side, I can create a date column. I will again color code it as gray so that people know that they don't need to change anything over here. And here I can put date as year, month, and I'll put in first day. Again, I will drag it down a little longer than what my data is right now currently, because later on it will be expanding, but as you will see, it will give error. So I'm just going to wrap it in side if error and return blank if nothing is found. Perfect. So here on the model forecast sheet, I want to bring in the latest date. It's very simple. I'll just put in max, go to the historic data, select the entire column, and it will always give me the max value. Later on, if the January data comes in over there on the historical data sheet, this will automatically adjust to January. Now from this date, which is coming based on the historical data or the latest historic data, I want to go 12 months back. The best way to do it is to use the edate function. I'll use edate, give this date, and I'll ask it to move 1 month back. Close the function, and now it goes back. Likewise, for the forecast horizon, I want the model to take this date and go 12 months forward. Again, I can do that using edate, and I will put in +1 and drag the formula rightwards. Now all these dates are dynamic. Also, I want to do the same for promo forecast and the price forecast as well. Here in the column headers, I will need the forecast horizon. So it's relatively simple because we've already set that up. I can simply link these cells to the headers that we have set up in column O to column Z. Once the forecast horizon in column O to column Z changes, these will update automatically. So I will link the cell AB2 to cell O2. Then I will drag the formula rightwards by selecting the entire range and using the keyboard shortcut Ctrl+R. And then I'll do the same for price forecast. Now let's test it out. I'm going to go to historic data sheet. Let's say we have the January 2026 data. For testing purpose, I will just put some dummy data for January 2026 in one row. If you will go to the model forecast sheet, you will see that the last 12 months actuals has been updated. Now it is from February 25 to Jan 26, and the forecast horizon has also been updated. It's now from February 26 to Jan 27. Don't worry about the empty values right now. These are showing empty because we just put a dummy value for SQ015 and did not update the full data for January 2026. But this test does show that if new data arrives, the forecast horizon as well as the last 12 months actual will update automatically. Now I'm gonna do Z here to go back to the original state. The model is almost ready. Now we'll run the model to test whether it works correctly across different forecast cycles. So starting with the February cycle, then we'll test it out for March cycle, and so on. But before we do that, it's important to build a few checks and balances and controls into the file. This helps ensure that users don't miss anything or make errors while using this model. For the model to run smoothly, there are a few key things that the user needs to keep in mind. The first and very important thing is that all the SQs that are there on the historic data tab and therefore are being considered in the forecasting scope should be there on the mapping file. If one of the SQs is not there in the mapping file, then it means that the forecast method will not be there for that SQ. And if the forecast method is not there, it will not show up over here, and ultimately it will not get qualified for the calculation of the forecast because the forecast calculation depends upon the presence of the forecast method. Also, we need to make sure that there are no duplicates in this particular column, because if there are duplicates, this means that there are two forecast methods for the same SQ and the system might not pick up the one that the demand planners are actually intended to be followed. Also, all the SQs should have a price and promo forecast. So on this particular sheet as well, we should have all the SQs that are in our planning scope or planning horizon. So right now we have 15, all of them are there. If one of the SQs is not here, then on the model forecast sheet, the price and promotion will not flow through. And if that particular SQ is designated as MLR, then that SQ's forecast will not get calculated. Also, having the price for all the SQs, even if they are not MLR, is important because later on you will see that we will calculate the value of the forecast as well. These are right now volumes, as you know, but we want to calculate the sales value as well. So we will multiply these volumes with the price later on. And lastly, the pricing and promo forecast sheet should be for the entire forecast horizon. Right now we have the pricing and promotion for 12 months, Jan 26 to December 26. Next month in February cycle, our forecast horizon will shift to February 26 to Jan 27. So this sheet will need extra two columns. One column where we add the pricing forecast and another column where we add the promo forecast. So these are a few important steps that the user needs to follow for the model to run correctly. To make this easier, it would be helpful to build a separate sheet that highlights if any of these steps have been missed. This way, for example, if some of the SQs that are in the forecasting scope are missing from the mapping sheet, a check will automatically flag it here on the check sheet. The user won't need to manually review or scan the mapping sheet every time they update the model. So let me show you what the final output looks like. This is what the end product is going to look like. Here I have the historical data. It still has only 15 SQs. This is the mapping table. And here I have built-in checks. So let's say if any of the SQ is not present on the SQ mapping table, we will get a check over here. I'll do Control Z now. Likewise, if there is any duplicated SQ over here, it will first of all show up here, but this list might get too long, so the highlights might not be visible. So I have set up a check over here as well. Then I have a for check that is all SKUs should have a price and promo forecast. Let's assume that we do not have a price and promo forecast for SKU number 15. If I come back, it will show me a check over here saying that SKU number 15 does not have a price and promo forecast. And also the price and promo forecast should be for 12 months. Let's say one of the months is not present. Our forecast horizon in this file is 12 months from Jan 26 to December 26. If let's say one of the months is not present, then we will get a check over here saying that this month forecast is not present. In the few upcoming lessons, we're going to see how we can build these checks into our model. Let's start off with building the first check, where we want to make sure all the SKUs that we have on the historic data sheet are present here in the mapping table as well. If any SKU is missing from the mapping table, we want Excel to flag it and show us exactly which SKU code is missing. This way, we can quickly identify it and add it without having to manually scan through the data. First of all, let's get the list of all the SKUs that we have on the historical data sheet. We already built a function for this purpose. It's called list all historic SKUs, so let's use that. Now I want that to have the list of all the SKUs that we have on the mapping table. So I'm going to use filter. I'll give reference to this array. I'll go all the way down. Then I'm going to freeze this array. Okay. And I will say that return me all the values that are not equal to blank or empty. And there we go. So far, the mapping table has all the SKUs which we have on the historic data sheet. If I remove, let's say, SK015 from here, you will see that it will disappear from the second array that we just recently set up. Now, I want Excel to do the following. I want it to go through the first array one by one and check whether each SKU in the first array exists in the second array. For this, we can use the xmatch function. In the first argument of the xmatch function, that is the lookup value, I'll pass in the entire first array. In the second argument, I'll pass in the entire second array. Excel will then go through each SKU in the first array, find its position in the second array, and return the corresponding position. As you can see, it's able to find all the SKUs except SQ015 because that one is not present in the second array. Now I only want Excel to return the SKU that is not found. We can do this in two steps. First, I'll wrap the xmatch function inside an isAny function. This will return true for any SKU that is not found in the second array. The isAny function is an information function. It evaluates the values passed into it and returns true if a value is NA, and false if it's a valid number or a result. So let's apply that here. Now in the second step, from the full list of SKUs, we only want to extract those that are not present in the second array, and the second array represents our mapping table. To do that, I'll use the filter function. In the first argument of the filter function, I'll pass in the list of SKUs from the first array. In the second argument, which is the criteria, I'll pass in the true-false array, which we just created using the xmatch function wrapped inside isAny function. What this does is tell Excel to return only those SKUs from the first array where the condition is true, meaning the SKU that was not found in the mapping table. And there we go, we get SQ015. Now if SQ015 is also added to the mapping table, This formula will return an error because there are no longer any missing SQs. So I'll enhance the formula by wrapping it inside an if-error function. If there is an error, I want the formula to return OK. Otherwise, it will return the missing SQ code. Right now, since SQ015 is missing, we see SQ015. Once we add it to the mapping table, the result will change to OK. Now let's simplify this formula even further. The first input currently references the range in cell J3. But J3 itself is generated using the custom function that we created earlier, list all SQs historic. So instead of referencing the range in cell J3, I can directly use that function here in this formula. Similarly, instead of referencing cell M3 in this formula, I can simply place the underlying formula which is used to generate the values in cell M3 over here. This is the formula that we are using in cell M3, so I'm going to copy it. And then I will place it in place of cell M3. Now let's take it further. We still have some intermediate references coming from J3 and K3. So I want to eliminate those as well by directly embedding their source formulas here. Starting with J3, I'll replace it with the formula behind it. Now for K3, we're using a filter function over here. So we've got two options here. Either I can copy this entire formula and slot it in cell O3, which we are working with, or I can create a reusable custom function. I'll go with the second option since I know that we're likely going to need this formula again later on. So I'll copy this formula, go to Name Manager, create a new name. I'll call it List All SQs Mapping Table, and paste the formula in here. This will make our model cleaner, and later on it will also be reusable. Now in cell K3, I can replace the existing filter formula with the custom function that we just created. Similarly, in cell O3, where we are setting up the check, instead of referencing cell K3, I can directly use the new custom function that we created. At this point, if I delete all the data from columns J to column M, the check in cell O3 will still continue to work. Now I'll copy this formula and place it in column J since that's where we want to display the check. Now let's test it out. If I remove a few SQs, say from SQ010 onwards from the mapping table, the check will immediately list all the missing SQ codes. And once I add all the SQs back in the mapping table, the result will return to OK. As a next step, I'll format the check cell to make it more user-friendly. If everything is okay, I want the cell to remain unhighlighted. But if any SQ is missing, I want it to stand out, so I would want to see it highlighted in red. This way, it immediately catches the user's attention and gives a clear visual alert. So I'll select the cell, go to Conditional Formatting, New Rule. Then I'll select this option, which says Format only cells that contain. And I'll say cell value equal to, in fact, cell value not equal to OK. So if the cell value is not equal to OK, I want it to format with a red color. I'll click on OK. Now, if I remove SQ015, it will show up as red. If I complete the mapping table, the check will go away and it will appear unhighlighted.